do that after proper setting. If you look at the printed fabric, take the cross section or the fiber and take the cross section, do you think the fabric or the fiber across the cross section has been colored uniformly? Yes or no? No. So, if it is not colored properly, that means it may have penetrated 50%, it may have penetrated 75%, it may have penetrated 25% in the diameter part of it. Then how do you calculate the shade? It is what you see, but what you see from the same recipe could become different if you change the time of steaming, and suddenly you find, oh, everything was same, shade is not matching because something else changed. Equilibrium is not reached. Equilibrium can be reached only if the same print is seen on the other side. The face and the back of fabric. Do you think any printed fabric's face and the back are same? They are not. So, even defining that this is percentage shade is a question. How do you define? You do not even know the weight of the fabric. You can measure it, but you do not know how much it has penetrated. If it penetrates 50%, shade will be different. If it penetrates 100%, shade will be different, although you have applied the same. That is the difficulty. So, you keep lot of things which are not in your control, but you want to control and you must control, and that becomes the difficulty level of the printing. So, it is not an easy process, it is definitely not an easy process. And so, when somebody says, well, I have done some print in my lab after washing, I am not sure you would ever like to wear that in the first go. And what is the question of is uniformity? At least from the face to back, uniformity is not needed. You do not want to print the back of the fabric in any manner, it will never look good, and so you do not. But you have understood the difficulty also. Then we say localized dyeing means you have to have boundaries. So, you have to make sure that particular color is only in that boundary, it does not go beyond. What have we done? We have done covering, we have made more wet, material wetting properties have been increased so that things can go. So, theoretically we do not expect when you put a drop of water it goes only across the fabric, it goes around the fabric also, it goes in all directions. How do you restrict that? So, you say, well, we will be using highly viscous material called a paste. So, as long as very highly viscous, it will remain there, then you dry it, it will remain there. Only when you are just about to say, well, it must diffuse, give certain amount of moisture, little bit of a dilution, and then it diffuses. So, you are hoping that it is concentrated, it is very small amount and very less amount of water, that means high concentration. Therefore, you do the control the spread, it is very important. If everything is right, the person had printed very nicely, everything was in the right place, but when it was getting fixed, something started diffusing, yellow going into the blue. So, you have another boundary of a different color which you never wanted. So, somebody will find out, so now finds it out or not is a different story, but the person who is doing the job is very unhappy that after all the hard work what you get is the wrong design. So, in this printing process, of course, you have to print and then you have to dry and fix. This is the most important step. All of them are very important steps, You make a mistake anywhere, it is all over. Drying, of course, you may have some leeway that you are just drying, removing the moisture, but you can, during drying and handling, if there is a crack appears because you have a film of a thickening agent which has been dried, then the moisture penetration through the crack will be different, and you might see after print you actually have a permanent mark which may not get fixed properly. So, you have fixation, which is important. You can do dry, steam. So, these days your steam also is atmospheric steam or superheated steam, so high temperature steam. Any of them can be used depending on which fiber, which dye combination you want, and then you wash. Obviously, you have to wash because you have added so many other things, which we will see, which were not part of your plan. You wanted only dye, but you have a lot of things. Wash and then dry. So, drying, fixing, like any other chemical processing unit operation, a lot of energy is consumed, but that's it, no problem. We have to consume energy. Unless that happens, it becomes a problem. So, this is the basic process of printing a textile fabric. Simple steps, essential. We've done everything, and you say now washing. Washing itself is a difficult task. There's so many colors very near each other, they are now going to come out. The question is, it's a very unlikely that 100% of all the color that you have added have gone into the fiber, and they are also fixed exactly in a manner in which you want to fix, and nothing will come out. Then the best thing. But that doesn't happen because every reaction is an equilibrium reaction. 90% on the favor of fiber, 10% not in the favor of fiber, or maybe 95-5, it doesn't matter. But whatever is unfixed is one will be washed, which will not just be the thickening agent or the auxiliaries which will come out, but the dye also comes out. The blue flows over the yellow flows over the white, and so anything can happen during this process. So, you have got to be very, very sure. When you do dyeing, you just wash. Just keep washing till everything has come out, and you say, well, now nothing will come out. Go ahead. The same thing you want to do it here, but you have to be very careful. The moment the dye comes out from any region, it should not go back to the fiber at any portion of the fiber or the fabric that we mean. And so, washing is a tough thing. So, everything that you want to do in a printing is a tough thing, although it is a simple process: print, dry, fix, wash, dry. Well, then there are fun things also. The fun things are that you can print in different ways, and they are called styles, and these three names must be in your mind: the direct, discharge and resist styles of printing. So, what is the direct style? Yeah, somebody will tell me, what is the direct style of printing?
Color onto the fabric directly.
Right. Like block printing. What do you say? Like block printing?
It can be block or screen or white.
Right. So, that is the technique of applying color, but this is a style. So, what it means is that you have a fabric, on this you are putting some design, color could be different. Yeah. So, whatever the design, you print it on the fabric, right? That is one. You can have 4 colors, so you will have 4 different times you have to work, so that 4 different colors and 4 different parts of the design become the main design. Can we print with a direct style on colored fabrics? Yes? Good. So, it does not matter, is a white fabric, grayish fabric, yellowish fabric, bluish fabric, you can just print directly if that is what the design is. Suppose you have dark black, jet black fabric and you want light lemon print on that, what will happen? It may not be visible at all. So, this style becomes relatively ineffective, and if that happens, then we have the other style in which we say, okay, we have a colored fabric and colored fabric generally deep dyed. If it is a light color, people would probably go for the direct style and you get the same design. If it is colored fabric, then you say discharge style, and what does it mean is that from the colored fabric you are going to be removing color from the design. And how do you do that? You destroy the color by, could be anything, generally reducing agent. If you take a reducing agent and therefore you have to select a dye, and I suppose you said I have dyed black with a wet dye, do the discharge for me. Will you be able to do that? No. Therefore, you get restricted. You get restricted that the dye which has to be discharged must be dischargeable. Only then you can use this style. Otherwise, if you work very hard, of course you can take an oxidizing agent to work very hard, like then bleaching, I will make sure that there is no color. You might find the fabric gets damaged, any other thing can happen. And so, normally we will choose dyes, because therefore you must know what is the design and what is the things are going to be used. Accordingly, you will choose the thing. If suppose somebody is adamant, no, in this style also I will like to use direct style, that means I am not going to discharge. Can you do that? Deep black shade, light lemon to be brought in, small dots, polka. Would you like to do that? Can you do that? You cannot, but you can. You can do that. You may not like it. What it means is that you print both, print the small, then print the big. You can still get two prints, two screens, but printing is costly. Printing is a costly process compared to dyeing and then discharging. So, that is one print. In this also you can have white discharge or a color discharge. It's up to you. But then again, selection of the so called colorant has to be very specific as to one which resists the discharge, the other actually gets discharged. Important thing is, when we say that this is what the process is, this is only principle. The selection of a dye and a process will still be a tedious task. Then you say I have discharged, you say it is not as white as I thought. Then you have to do something else to look so that it looks whiter. So, it is not something which you say, well, this is it and end of the game. It actually starts from here. In the resist style, which are quite popular, even before a lot of things were done, you do the reverse. And that also sometimes you may like to do the reverse because some of the patterns it may be difficult. For example, there is something called batik. So, irregular patterns to be created. So, you do something and then dye on top, or chemical resist where you print in a manner that the dye cannot get fixed. So, invariably you may be able to get like tie and dye, total mechanical thing. You get beautiful designs. So, chemical, mechanical resist systems have been developed for various styles and various kinds of designs which can fall in the category of resist style, right, like what you said. So, what he was talking in the beginning of this small discussion was the methods of printing. You can use any method to adopt any style. Method would depend again on whether you are doing high production, low production, automated systems, or just simple things. So, I was talking about block. Yes, there is a block printing method, batch wise process. One can think of automation in blocks also. One can have a machine which can have blocks and print and this moves and then you print and the other moves. You can do that also, but generally people are doing hand block printing, some traditional stuff, but you can do all kinds of things. Roller printing becomes a continuous process where the design is etched on the roller, and now it does not matter whether you discharge or a resist or a direct, it does not matter. Style is unimportant. It is a costly process. Generating a roller design on a roller is a costly process. Screen printing is one of the most popular things. You can have a flat screen, or rotary screen printing machines. The flat would be considered as semi-automatic systems or could be completely manual, and rotary is generally continuous process, where like a roller printing, a rotary screen is a continuous process. And of course, there are many things that you can do, like a stencil. Take a stencil, paint it the way people keep painting things, you will get a design. You can do spray, you can get the things. So, you can actually look at many other methods, and these days the kind of methods that again we will be talking, the transfer printing is a method that you do some printing somewhere else and then transfer onto textile. All the things have been done somewhere else and then you transfer. Or now we are looking at digital printing. So, all those things will be also methods, transfer, digital, they are methods, and these methods are in some way fascinating to begin with, which are different from whatever is being used, and so we will spend more time here. I think today we can stop here and then we will take up later the other aspects of the conventional printing, which are as serious as important as it can be. Thank you.
Hello everyone, we are discussing the nature of stress strain curve for different material. Okay. In the stress strain curve we can get various parameters like initial modulus, yield stress, yield strain. Okay. This we have discussed, and the total nature of curves, this stress strain curve we have discussed. Okay. So, this region beyond the yield point. So, after that, the due to rearrangement of the molecules. So, this curve again it increases, and the nature of curve depends on the molecular structure of fiber and the fiber structure of yarn. So, if the fibers in the yarn are aligned towards the axis, then stress strain curve will be entirely different than the fibers which are twisted. So, depending on the twist characteristics, the stress strain characteristics will change. Now, let us see different fibers, different yarns, how do they change, how their stress strain characteristics change. So, this is wool, and wool has got this stress strain characteristics, where with the small increase in stress, it gets strain, very high strain. So, it has got very high extensibility. Okay. But on the other hand, flax has got very less extensibility. So, this is mainly due to the difference in their molecular structure. Now, for same fiber, okay, polyester. So, polyester, it is a low oriented polyester, partially oriented polyester, and fully drawn polyester. Okay. So, in case of same fiber, if we can orient the molecule, okay, the stress strain curve will totally change. So, this is basically a low oriented polyester, as we have discussed earlier. This nature is mainly due to rearrangement of the molecule. Okay. So, molecules get straightened, aligned towards the axis. So, during that time the strain is very high. Okay. But in case of fully drawn yarn FDY, it has been aligned, oriented. So, that is why it takes higher stress with smaller strain. Okay. So, rigidity of that FDY is much higher than LOY, okay, which is expressed by initial modulus. Now, another example where normal cotton is treated, chemically treated. After chemical treatment, both stress and strain normally changes. So, here it shows the cotton becomes weaker, okay, and it has got its the lower breaking stress. Okay. So, the stress strain curve also changes with the chemical treatment. Now, as I have mentioned, with the increase in twist multiplier for staple yarn, it gets changed, the stress strain curve, stress strain characteristics get changed. Now, here we can see that in green curve it shows it is a say normal yarn, okay, normal yarn, and with the increase. So, here it is this is the characteristics, and when the twist is increases. So, TM to TM, this is TM1 which is lower, and increase to TM2, twist multiplier 2, then twist multiplier, it is the highest TM. So, as the twist multiplier increases, the fiber, the yarn become stiffer and stiffer. That means, initial modulus is increasing, because the fibers are packed together, packed in a better way. Okay. For better packing, due to this better packing, that initial modulus increases, the yarn becomes stiffer. Okay. But that as the twist increases, initially this is the the strength increases. This is due to the increase in the frictional contact, but beyond certain point, when we move beyond Tm2 to Tm3, what happens due to the obliquity effect of the fibers. So, actual final breaking stress drops, although the initial modulus is higher. So, this total yarn characteristics, total stress strain characteristics, looking at the stress strain behavior, one can predict what is happening there. So, these are the different factors which affect the stress strain behavior of textile material. Now, we will discuss another terminology which is called work of rupture, or it is called that the area under the curve. Work of rupture is nothing but the energy required for break, okay, due before its rupture. So, it is a measure of toughness of material. Okay. This is work of rupture is very important for many applications. Like one example, in mountaineering rope. Okay. So, it is not that the strength, the stiffness of the material which is important, which is the important is that how much shock, how much energy it can absorb before it fails. So, that is important. So, there are many applications where the energy required to before breaking, like in weaving, it is not the strength of the warp yarn which is important, it is the work of rupture of the yarn which it is important, because during the shading and beating operation, the yarn has to actually withstand the energy, okay, energy required to break, that is important, and it is not important that which is the stiffer one or which is a stronger one. A strong yarn, very strong yarn with very high stiffness, that means very low elongation or low work of rupture, like there is two yarns we can talk. This is cotton yarn, another is suppose steel ware, strength is very high, but stiffness it is very stiff, and here it is say high carbon steel ware. Okay. Now, here if we see the area under the curve, what is the area under the curve? For cotton, this is the area under the curve. That means, energy required to break the cotton fibre yarn will be this one. But on the other hand, if we see the steel wire, the breaking energy required will be this much. Okay. That means, the cotton requires higher energy than steel, although steel is extremely very high. So, the question is which one will be suitable for weaving. If we use the steel wire in as a warp in weaving, it will immediately break, it will start breaking, its performance will be very poor, and as compared to cotton, cotton will do much better performance, okay. It will have much better performance. So, not only in weaving, there are many other applications like a parachute. In parachute, even in the parachute fabric or the rope, when the paratrooper jumps, okay. So, the work of rupture, that is the energy before it breaks, it has to be very high, otherwise it will fail. Okay. So, in that way textile material has got its advantage. Okay. So, it is the energy or work required to break a specimen that means the area under the load elongation curve, that is area of the shaded zone, that is the work of rupture. Now, we can see the animation here. This is the load elongation curve. We must be very careful. This is the area under the load elongation curve, not the stress strain curve, because it is the energy, okay, load and that is force and multiplied by the elongation, and this is the work of rupture. Okay. So, area under the load elongation curve. Now, what will be the unit of the load area, unit of work of rupture? So, unit of work of rupture is the gram force multiplied by centimeter. That is force multiplied by distance, that is the work of rupture. But for practical purpose, for comparison purpose, what we do, this is the work, okay, because W is proportional to the cross section, okay, denier. W is proportional to denier and also its a length. That means, if the denier is higher, it is a denier, it is a coarser denier or coarser text, then it will be the work required, force required to break will be high. Okay. That is why the W work is proportional to the denier, and also as the initial length of the specimen is high, then the work requirement will be high, because that extension will be high. So, that work of rupture will be high. So, the work of rupture is actually, it changes with the denier proportionally and with the initial length. That is why for comparison, if we divide these things with the denier and centimeter length, in that case, like for we have seen earlier, the stress is divided by the linear density, the gram force is divided by the text, just for comparison purpose, that we have seen. Here again, if we divide the work of rupture by denier and the length, so that we can compare, okay, we can compare the and if we rearrange this equation, then the centimeter will be cancelled out, ultimately will remain, it is a gram per denier or gram per text. So, if someone says that okay, what is the practical, the unit of work of rupture, it will be gram per denier. So, effective unit will be gram per denier or gram per text for comparison. Okay. Next is that work factor. Now, work factor, the concept of work factor is just to understand the nature of curve. The curve can be any textile material, the curve can be like this or can be like this. Okay. So, for a very stiff material, the curve will be initially it will have higher stress, this is the stress strain. So, initially it will take higher stress, then gradually it will break due to the bond breakage and all this, it will have another like wool. So, initially there will be extension, then it will increase. Okay. and there is a ideal curve which will increase with the, say there will be straight line, that is ideal material, okay. That is elastic material which will straightway increase, although the textile material will not follow this one, either this will follow this type of curve or this type. Now, the work factor gives an idea, by if we know the work factor value, it gives an idea about the nature of curve, whether the curve is following this type pattern or this type pattern. So, always we do not have the curve in front of us, but if we have the work factor value, then we can tell it is the nature, we can actually guess the nature of curve. Now, let us see the animation here. Now, this is the ideal curve, okay, where the work factor is nothing but the area under the curve, this area under the curve divided by breaking stress and breaking strain. This is the breaking point. So, what is the area under the curve? Area under the curve is half of breaking stress and breaking strain. So, this is the area under the curve, half of the this base and altitude, okay. Altitude, half height is that stress and base is the strain. So, and divided by the breaking stress and breaking strain. So, in that case if it cancelled out, so it remains half. So, work factor will be half in case of the ideal elastic material, okay. Now, another material where this is the there is an increase in this. So, here work factor will be, what will be the work factor, because area under the curve, area under the curve will be more than the this straight line, the actual area under the curve will be more, okay. So, and divided by the breaking stress and breaking strain. So, that means the work factor will be more than half, okay. And on the other hand, if we see the other type of curve, it shows with the blue line. So, this is the curve where it is a work factor, here it is a less than half. So, the by knowing the value of work factor, we can guess, we can actually predict the what type of nature of the curve, okay. So, if the curve follows Hooke's law, okay, the material follows Hooke's law up to the breaking point. So, it there is no bend, then the work factor will be half. So, it is area under the curve divided by breaking stress and breaking strain, okay. And it describes the nature of the curve numerically, okay. It is not, if we do not have the curve in front of us, but numerically it is, if it is the value, then we can guess, we can tell the, okay, this is the work. So, work factor of 0.4, if it is asked draw stress strain curve of a material with work factor of 0.4. So, that in that case you have to draw curve like this 0.4, okay, work factor of 0.4, okay. Straight line work factor of 0.5, work factor of this 0.6. So, this type of actually problem it is given in the exam. So, it is given that the curve, nature of curve, different nature of curve, and tell the work factor, whether it is a this 0.4 or some values will be given, we have to tell the work factor, predict the work factor, okay, logically. Now, the term elastic recovery, what is that? It is the property of a material by which it tends to recover to its original size, okay. So, any material after extension, it normally it tries to recover to its original size and shape, okay. But there it may not be 100%. So, by the term elastic recovery, it is actually one can see, one can actually calculate the how much deformation it will try to gain to its size, original size and shape. Okay. Now, this is the yarn. Suppose yarn, initially the yarn length is AB, AB is the initial length. Okay. Now, it is a load elongation curve. Now, we are extending from B to D, we have extended, the load has increased. Okay. This up to this point we are not breaking the material, and after that we release the material. After releasing, its load is gradually reducing. Okay. And then it is reaching up to the point C, it is not coming to the original point. Okay. So, this is the deformation, it is called plastic deformation. Okay. And this is the deformation, it is called elastic deformation. Okay. Where it is recovered. Now, we can see the animation here. Now, it is increasing. See, this is the initial length of the material. So, suppose it is yarn, AB is the initial length. Now, it is extending and it is increasing and it is reducing. Okay. Now, this is the distance we can calculate. Now, AB is the original length, AB original length, CD okay, is the elastic extension, CD is the elastic extension where it is come back, and BD is the total extension from B to D, it is the total extension, and BC is the permanent set. Okay. That is plastic deformation was there, and from there one can calculate So, elastic recovery is the CD, what is the recovery divided by total deformation. So, CD by BD, and for perfectly elastic material there will be total recovery, that means BC will be 0. So, BD will be equal to CD, that means BC is 0. So, in that case for perfect elastic material elastic recovery will be 1, and for perfectly plastic material, that means CD it will not come back, it will remain at that point. Okay. That it is called at it is 0. So, elastic recovery is 0. So, textile material, most of the textile material they are neither the plastic material nor the elastic material, they work on the viscoelastic. So, it will actually come back, but it may not, it will, there will be definitely some deformation. Okay. If it is extended beyond the yield point, but if it is extended within the Hooken region, then it will come back. Okay. That is why for most of the low stress mechanical characteristics it works under within the Hooke's zone. So, this is AB is the original length, BD is the total extension, CD is the elastic extension, CD is the elastic extension, that means it is recovering, and BC is the permanent set, and elastic recovery is CD by BD, CD by BD. Okay. For perfectly elastic material this BD will be equal to CD because it has come back. So, BC will be 0. So, perfectly it will recover. So, elastic recovery is 1, and for perfectly plastic material that is its a CD is 0. So, elastic recovery will be 0. Okay. So, there are different applications not only in technical textiles, but in the daily apparel also, that bagging effect of garments, okay, dimensional stability, it changes with the stress characteristics. So, this even with the different technical application, so we must know the elastic recovery characteristics. Next is that, so we can calculate the yarn specimen, okay, of 200 millimeter extended by 10% when loaded with 500 centinewton force. Okay. That means, when 500 centinewton force is applied, okay, the 200 millimeter yarn is extended by 10%. Okay. The length of the specimen after removal of load was found to be 202. So, after removal there is a deformation, that is it is length 202, that means it was initially 200, now it has become 202. Calculate the percentage elastic recovery of the yarn. So, 200 was the initial length and extension was 10%, loaded 500 by 500 centinewton, and final length is 202. Okay. Here the load value is not required because extension value is known. Okay. So, extended length will be, that is 10% of initial length, original length. So, 10% of original length it has increased. So, it has become 220 millimeter, and the final length has become, it is that is the total extension is 20 millimeter, and elastic extension is that extended length by final length. Final length was given. So, elastic extension was 18 millimeter. So, 20 millimeter is the total extension and elastic extension is 18 millimeter. That means, the ratio of these two will give us the value in percent, okay, multiplied by 100. So, it has become 90%. So, 90% elastic recovery is there. So, one should practice this type of numerical, this is the answer. Next is that time dependent effect. Okay. So, time dependent effect is that, so here its load is not increased continuously. In earlier stress strain we have seen stress is, load is increasing and strain is taking place, but here the material is loaded once, okay, and it is kept at that loading condition for a long time. So, this type of situation is there in many technical applications, like in geotextile, for any application where the material is under constant load for long time. So, for that we must know the stress strain behavior, okay, the strain behavior, time and strain behavior. What is that? Load is fixed, that this is for geotextile under the ground, it is continuously loaded. So, we must know the its strain characteristics, so that we can predict whether it will fail or not. Okay. So, that characteristic is that time dependent extension, it is known as the creep. Okay. Now, once it is loaded, there will be two types of extension. Suddenly we are hanging a constant load, it is not that load is increasing continuously, increasing at certain rate. Okay. Suddenly we are hanging certain load, okay. Here as per this curve it is loaded. So, during that time there will be one instantaneous extension. This is the zone where the material will get extended instantaneously. Then after that it will not stop here, it will keep on extending. Okay. So, if we see in normal load elongation curve for that particular load value, the extension could be like this, could be up to this point, this is the extension up to this point. Okay. But if we let the load remain for a long time on the material, it has been observed that there will be again continuous increase in elongation, it will keep on elongating. This elongation is known as the time dependent elongation, is known as the creep behavior. This is due to the molecular rearrangement, okay, of the, and after that, after certain time, if we release the load, okay, again it has become 0, and it is not that immediately it will come back. So, it will try, it will come back slowly. Initially there will be immediate response, immediately there will be sudden drop in strain, suddenly there will be contraction, but gradually it will come back, try to come back, but after certain time there will be no reduction in shape or size. So, this difference is known as the permanent set. Okay. That is due to, that means there will be permanent deformation in the molecular structure. Now, we will discuss some important factors which affect the tensile result. Okay. The tensile result means that for same yarn, if we change same textile material, if we change these parameters, the value, load value will get changed. Suppose there is a yarn, this is a yarn. Okay. Now, the yarn cross section, its unevenness will definitely be there. Now, yarn will break in its weakest point. Now, if we can plot the yarn, the strength, theoretically if we can get the yarn strength at different point, okay, the strength of the yarn will be like this. At different point, the actual strength will be like this. Okay. So, this is say S1, S2, S3, these are the weakest point. And now, it is a specimen length. We can test the tensile test by, this is the yarn sample, this is the top jaw, this is the bottom jaw, and here suppose it is a length L1, length L2, length L3, like this. Okay. If we take this, the strength, if we measure the strength of yarn by taking this total length, by taking the total length which is L1 plus L2 plus L3. Now, if we take, suppose this is the top jaw, here it is a bottom jaw, this length is the, it is called, it is L1 plus L2 plus L3. If we take this length, so here as per this picture S1 is less than say S2, okay, is less than S3. So, S1 is the lowest value, followed by S2 and S3 is little bit high. Now, if we take the gauge length as L1 and L2, L3 a total length if we take, in that case what will be the strength of the yarn? The strength of the yarn will be S1 if we take, that means in this case the strength of the yarn is S1. Now, if we take the yarn, another test if we do, if we perform in that case. So, here another test, it is test 1, another test if we take, that we are now trying to break, we are trying to reduce the size, reduce the specimen size. So, this is L1, L2, L3. Okay. Now, if we test the L1 here, this is L1, what will be the strength? Again the strength should be S1 lowest. Now, if we test the say L2, then the strength will be S2, which is more than S1. Again if we take the S3, it will be S3. So, in this way if we can reduce the size. Okay. Now, here if we see with the smaller length, if we test, the mean strength will be, so L1 and L2 if we take, the mean strength will be S1 plus S2 by 2, because in this portion the strength will be S1, next portion the strength will be S2. So, the mean strength if we take, the strength mean strength will be S1 plus S2 by 2, which is numerically more than S1. So, that means if we reduce the size of the specimen for the same yarn, the actual the strength which is actually reported strength will be more, but the yarn is same. So, breaking strength is the load at break at the weakest point of a specimen of a specified length. Okay. Now, for length L1 the breaking strength is S1 and so on, S1, S2, S3, S4 like this. Okay. Now, with the gauge length of O dash, the breaking strength would be S1, because it will break at S1 point. When the test, we test two halves, so we can actually divide into two halves. One is O double dash, another is O double dash O dash. So, O dash we are dividing into two parts. In that case we are getting S1 plus S2 by 2, because we are taking two values and then taking the mean. So, that is how, so we are getting S1 plus S2 by 2, which is numerically it is more than S1. So, that means it is in any standard test method, as we have discussed when we are discussing the standardization of testing. So, the length of the specimen is specified. Otherwise, to show the higher strength, one would like to test the material with a lower gauge length, and to show, to prove that yarn is poor quality, he will start testing with the longer gauge length. So, that is why gauge length, effect of gauge length, specimen length is very important to be fixed. Okay. So, this specimen length and irregularity. So, hence, here if the irregularity is more, so 5 the yarn is having higher irregularity, in that case S1 and S2, the difference of S1 and S2 will be more. So, if the irregularity is less, in that case S1 and S2 will be very close, that means the effect of fiber, the specimen length will be less. Okay. So, hence by testing yarn with shorter length, the apparent yarn strength has increased. Okay. This effect is known as weak link effect. So, yarn breaks at weakest point, and as we go on reducing the gauge length, apparent strength of the material will increase. Okay. So, for more irregular yarn, as I have explained, this weak link effect will be more, because the S1 S2 difference will be more. Okay. Hence, by adjusting the gauge length, the test result may be changed. That is why for any standard test, that gauge length has been fixed. In any testing, any tensile testing, gauge length is very important. Okay. It has got direct impact on the test result. So, standardization of gauge length is important. Now, you can say specimen length and irregularity. So, this is the regular yarn, blue one, it is a regular yarn, and this red one is a yarn which is irregular. But if we see that this yarn with a higher mean length, mean strength, still the regular yarn with little bit lower mean strength is better. For processing point of view, slightly lower average length with regular yarn is better. So, that is why for particularly in weaving, for warp yarn, its irregularity is very important. So, we normally do not, it is difficult to measure the strength irregularity, because strength value is there, strength CV is there. So, which one is important, strength CV or strength value? So, first for weaving, particularly in warp yarn, it is the strength CV which is important. So, two parameters are given, two yarn, one yarn is weaker yarn, little bit weaker yarn, but better strength CV. One should actually go for the better yarn, better irregularity with a little bit lower strength. Okay. Now, here this Pierce has given actually empirical equation. He has derived empirical equation which shows the effect of specimen length. Okay. Effect of specimen length on strength. Now, let us see carefully here. SL is the length of yarn, okay. Mean strength of SL is the mean strength measured at the gauge length L. Okay. Higher SL is at lower length. So, SL is actually mean strength of yarn measured at the length L, and SRL is the mean strength of yarn measured at length RL. What is RL? That is R times of L. Suppose if L is, say L is 10 its value, so 10 centimeter. So, RL, if it is RL is say 20, so R will be 2. So, 2 times of 10. So, SL is say S 10, suppose 10 at 10 centimeter gauge length, the strength is SL. At 20 centimeter gauge length, the strength will be SRL, where R value is 2. That means, the SRL will definitely be lower than SL always, because the gauge higher gauge length will result lower value. So, SRL is the value which is lower than SL. Okay. So, that means, this value will be less than 1, SRL by SL. So, SL minus SRL equal to 4.1 multiplied by 1 minus R to the power minus 1/5 multiplied by, this is the standard deviation. Okay. The standard deviation of breaking strength. The standard deviation of strength, okay, it is a sigma L. This formula has been derived by the, this is the empirical formula has been derived by Pierce based on large number of experimentation. Now, just by rearranging here, what we can get is the SL is the length, SL is the mean length, mean strength, sorry, SL is the mean strength of yarn at length L. Okay. Now, we divide both the term, both the sides by SL. So, 1 minus SRL by SL, and here this right hand side term will be that sigma L, that is your, it is a standard deviation by the mean strength, standard deviation of strength by mean strength multiplied by 100, it will be the CB percent. So, that means, it will that standard deviation by strength will be CB percent by 100, the CB percent by 100. So, this term, this has been rearranged in this fashion. So, this is the equation. So, here from there we can predict the strength at different gauge length. So, this is the term here. Now, here what we can see, SRL, as we have discussed, its SRL will be less than SL. So, the ratio. So, from this equation, if we just rearrange this equation once again, we will get this equation, that means SRL by SL equal to 1 minus this within bracket 4.2 and this value. Okay. Now, here if we see what will happen if R is 1, suppose R is in this equation, R is 1 means at the same gauge length we are testing, we are not changing the gauge length. R is R1 means we are not changing the gauge length, R is 1 here. Okay. Now, what will happen, R is 1 means this value will be 1, okay, and this total value will become 0, 1 minus 1, this total value will become 0, that means SL equal to SRL. That means, for same gauge length it is predicted that the gauge length, if we keep gauge length, the mean length will be same. Okay. We are not taking care of other factors, here we are talking only specimen length. Now, let us see what happen if we increase the RL, R value. If we increase the R value, this R value, so there will be some positive value here, there will be some positive value. So, this value will be reduced, will be lower value. Okay. This, if we increase it from 1 to some other value, so this value will be, earlier it was 0, now what will be the value? It will have some value, some parameter, this value will be more less than 1. So, earlier it was 1, so it is less than 1, so that it will have some positive value. So, that means 1 minus some positive value. So, this value will reduce, okay, as R value, R is increasing gradually. So, this value will also increase, with the increase in R, this value will also increase. So, this right hand side value will reduce, will be lower. So, SL value will, SRL value and L is constant. So, S R L value will reduce gradually. So, that means with the increase in R by S R L by S L will reduce. So, this we can get. So, if we know V and S L, one should be able to predict the S R L. Now, if the variability, we have seen the variability, if variability increases, that the yarn strength is reducing. Okay. Now, with this equation here we can see that suppose Cu percent is increased. If Cu percent increases, so this total value will increase. Okay. That means this value will decrease. So, SRL by SL will also decrease. So, this ratio will decrease, SRL by SL, this ratio decreases with the increase in the R value, that is R value means, which means it is the specimen length, and the V value is nothing but the specimen irregularity. So, with the increase in irregularity and the specimen length, this SRL by SL actually reduces. Okay. So, that means we get the lower strength with the increase in the gauge length and with the increase in the variability. Now, another important parameter we will discuss, it is a rate of loading and time to break. So, the tensile characteristics, the strength of the material, it changes with the rate of loading. That means, at the rate at which rate we increase, rate of extension, rate of loading. So, that changes the tensile characteristics. Earlier we have seen with the change in the gauge length, the tensile strength changes. So, apparent tensile strength changes. Here also, if we increase the rate of loading and time to break, so then the tensile characteristics will change. So, most textile materials show an increase in breaking strength with the increase in rate of extension. Okay. So, with the increase in rate of extension, the breaking strength will it changes together with decrease in extension. That is the nature of any viscoelastic material. Okay. Textile material is one of the most important viscoelastic material. So, due to viscoelastic nature of textile material, they require certain time to respond to the applied stress. So, due to this, the rate of loading, it affects the rate of loading. Okay. Different type of textile material like fiber, yarn or fabric respond differently depending on the structure. So, but in general the structure is like this, it is called spring dashpot model. So, in the spring dashpot model, if we see carefully here, it has got two components. This is the simplest model where these are in parallel, spring and dashpots are in parallel. The spring equation is that spring, when we apply force F on the textile material, this is suppose it is a model for yarn or any textile material. So, here it is any textile fiber also. So, here if we apply force, it has got two components, F1 component which is actually represented by spring, F2 component which is by dashpot. So, for spring the equation is that force increases with the extension. Suppose we are extending by x. So, the force increases with the extension, force is proportional to the extension. So, here F equal to K1x, the K1 is called spring constant. So, as we increase the extension, so the force will increase, it is a proportionally. But in case of dashpot, what happened? The equation is that the force increases, but with the with the rate of increase in rate at the rate of extension increases. But in case of dashpot, if the rate is very slow, rate is low, then dashpot will actually exert very low pressure. Okay. So, if it is very low, then force will be very less, but as the rate increases, the dashpot will actually exact very high force. So, that is due to this dashpot, so this K2 is dashpot constant. So, it is proportional to the dx dt, that is the rate of extension. So, as the rate of extension increases, so due to the F2 component, the textile material actually exert more force. Actually that is why the due to the increase in rate of loading or rate of extension, the tensile characteristics, apparent tensile load increases. Okay. So, this picture shows that the rate of at lower rate of extension, this is the curve, and the same material with the higher rate of extension, it has become stiffer and it shows higher strength. Okay. Now, we will stop here, we will continue with this discussion in the next class. Thank you.
So, we are ready for the next session on this printing lecture, and what we have covered in the last one is this: what is printing, how close it is from the dyeing, what are the basic steps involved like printing, drying, fixing, washing, styles of printing and methods of printing. This is what we revised. Now, in the lecture 2, we will look at the essentials, ingredients of a printing paste, and one of the essential obviously is the color. How many types of colors are there, what interactions that they have, all that is important from the point of view of printing as well, like it was for dyeing, right. So, if you look at the essentials, we have colorants, which, as we said, of course, it has to be supported by what we call as a printing paste to increase the viscosity, because we want to keep everything in the boundary. It is also sometimes known as thickening or thickening agent. Okay. This is how the life goes. And of course, you will require a large number of auxiliaries to support this printing process. All right. Although we will not concentrate on auxiliaries so much, we will spend some time on colorants and just revise as to what we had probably understood before taking a printing class. So, in the auxiliaries, one of the auxiliaries we are quite familiar is called the wetting agent, right. The reason why we use a wetting agent is to reduce the surface tension, mix things properly, because most of our action is going to be aqueous, water based, and therefore, what you would require is some amount of reduction in the surface tension of the systems. So, penetrations becomes easy. We are also quite sure that whatever we talk about, it is going to be a viscous paste, and a viscous paste obviously will have a difficulty in penetration. Also, we said there will be humectants. Humectants are required, again, as we said, it is a small area, small volume, concentrations are high, How do you get the water, because we have already dried the fabric, and so during the steaming process, during what we call as the fixation, whether it is a dry heat, superheated steam or atmospheric steam, you would get some moisture from the environment, and that moisture is going to be absorbed as such, or maybe the humectants are going to help them. The other important thing, of course, could be solvents, particularly those dyes which are not so much water soluble or their solubility is slightly less, like a dispersed dye for that matter, or wet dyes for that matter, azoics for that matter. And so, you may require additional solvents which may help it to remain in solution form. As we said, that unless and until the dye is in a molecular form, it will be very difficult for it to penetrate, diffuse into things, unless and until we are talking about pigments. Okay. Other auxiliaries would depend on what type of agent, what type of dye that you actually want to use. For example, if the dye is an acid dye, you may require acids in the printing paste. If it is, let us say, reactive dye, gets fixed in alkaline medium, so you may require alkalis. If it is actually wet dye, so you may have oxidizing agents or reducing agents as auxiliaries which you required in the whole process of printing. If you are looking at oxidation colors, you may actually have some amount of catalysts to be used, and dispersing agents would be required if we are using, let us say, a dispersed dye, because dispersed dye initially is dispersed and then of course part of it gets dissolved and then get diffused, and you get the molecular form of the dye which penetrates. Defoaming agents, foam gets generated because you have lot of stirring being done, and it is a viscous system, and if suppose lot of foam gets generated because you have a surface active agent which is called the wetting agent, and you must have seen whenever you do lot of agitation in any liquid system, when there is a soap or such detergents are available, lot of foam gets generated. It may not be the same situation here, but if the foam or the bubbles get generated and they are trapped in the paste, and when you actually do the printing, and they would burst at wrong time, and then the design will have issues. So, you may be using defoaming agents. So, there are many auxiliaries which are definitely required based on which type of a dye fiber system you are going to be printing. So, as I said, we will spend more time on colorants because they are our mainstay. So, when we say colorants, you have dyes and you have pigments. Now, whether this colorant has to be used as a pigment, in that case you will be supporting its fixation by some other mechanism, but if it is considered a dye, it must go through some dissolution process, and therefore, its interaction is going to be important. Theoretically speaking, the same dye which is be used for dyeing and same dye fiber interaction which is valid for dyeing process is valid for the printing process as well. If there are different requirements, let us see if we can find them, identify what requirements are there. So, a colorant is a compound which has a group which we call as a chromophore. Some of the popular names here you can see are azo, anthraquinones, keto, and others which I have not listed, you must have seen before as well. So, this is the stay, the color is because of chromophore. If the chromophores are not there, the compound is not colored, and that is one of the ways we can see when you reduce, let us say, a wet dye, the chromophore is broken and the color just goes off. In most cases it becomes pale, so major color is lost. So, these are the most important part of the colorant, which let us say it could be dye or a pigment. Chromogen is another supporting compound which obviously contains the chromophore. Now, these type of the body, main body of the dye or a pigment is the one which holds the chromophore, but also with the fiber it must be interacting. That is, when we talk about affinity towards a fiber, then some of these things can define. If you look at the size of a direct dye, if it is large dye, most of the molecule is not a chromophore. It is just a support system. It goes inside and does not come out because it can form some bonds, let us say hydrogen bonds with or van der Waals forces with the fiber molecule. And so, this type of a thing which is called a chromogen is the body of the whole molecule which supports the chromophore, but also helps in absorption. Then there are oxochromes, which are smaller functional groups which can be attached at para, meta positions, ortho positions of a dye molecule. They can change the tone. Let us say a blue can be a different blue or a red can be a different red if we keep playing around with some of these groups. This whole science is called the molecular architecture. So, a dye molecule has its own architecture, and based on these groups you can actually play around and actually synthesize a new dye molecule which may have certain interesting shade palette. And so, these oxochromes are also very important as far as they will be part of our dye. And yes, most of the dyes and also whether they are through printing or dyeing process would be applied through aquaspedium. And so, these solubilizing groups are the ones which help the dye to get solubilized in water. It is not that you can solubilize them in any solvent, but we are looking at groups like SO3 Na, which is sulfonate. So, they are ionic groups attached with dye molecules. So, the solubility will depend on how many such molecules are attached, what is the molecular weight of the dye. If the molecular weight is very large, obviously solubilities are not going to be very high. So, you have more solubilizing groups, and so you do the play around with the architecture of the dye molecule. Now, this question is that what type of colorants are available. So, there are large number of colorants that are available. All of them theoretically can be used for printing as well. Directs, if you look at direct dye, what is the problem with the direct dye? It was one of the easiest dye to be dyed, generally for cellulosic material, but people were not very happy with it because it was easy to dye and wash fastness was low, easy to come out of the fiber as well. It is not that every direct dye has low wash fastness, but large number of them have low wash fastness, and therefore, you may not like to print with direct dyes, because printing is a costly process. You have to do a lot of exercise, and at the end of the day, if anything wrong happens, then you are not going to be very happy. So, that is one dye, unless and until there are certain shades and certain types of dyes which definitely are very important and very nice, phthalocyanine based dyes for that matter. One can use direct dyes, but generally we may not. Reactive dyes, of course, reactive dyes, the name suggests that they can react with the molecule, so the wash fastness is going to be high. right? They make covalent bonds, right? And so, they are good for us definitely. So, people would like to use reactive dyes. Wet and solubilized wet are two combinations which people use. For printing purposes, wet is a good color, because after you have done the whole process, it becomes insoluble, and so definitely wash fastness is high, and other fastness is also very good. Sulfur, sometimes because it's cheap you might like to use, but it's also insoluble. But most people may not like to use sulfur as such. Sulfur is used for dyeing, but nobody can stop you for using that. Acids, metal complex, basic, that is the cationic dyes, and dispersed dyes are the ones which of course are used. And then there are pigments, organic, which are the like dyes which are insoluble. So, they can be pre-synthesized molecules as a pigment which will be fixed as a pigment, or they could be generated in situ while you are actually doing this whole process, the pigment get generated. That is one. And inorganic, of course, you can use some of the inorganic compounds which give certain types of shade which may not be easily available, easily synthesized in the organic, particularly in some cases the fastness properties may be also very good, and so you may like to use pigments. Let us first look at our revised, as I said, this is a revision. So, normally what would be happening is that you dissolve the dye in, let us say, water. So, we have water soluble dyes. So, in a normal case, from solution to the fiber surface, the dye goes, and then once it reaches the fiber surface, that is governed by, shall we say, affinity forces, and once they reach the surface, then the diffusion takes place depending upon the temperature, agitation and such conditions. In printing you have no scope for agitation, so you only believe that the dye definitely likes the fiber and therefore it just keeps moving in, right. This is what is going to be more important. And then of course fixation. Now fixation, if it is a reactive dye, we talk about covalent bond. If it is not a reactive dye, then it could just be van der Waals forces, hydrogen bonds and what have you. It's just like trapped inside the fiber and then does not have a chance to come out. So, you could be trapping a big molecule inside the fiber. Once it has gone in, it has got certain kinds of interactions, and because of that it would remain within the fiber. There are some dyes like dispersed dyes and polyester. It just goes in from aqueous medium which was solution to a solid medium which is also behaves like a solvent. It can be anywhere. You see, the property of a solvent or a solution is that the concentration of a dye at any given point and any given place is same, right. That is what the solid solution means. That is the solution. That means the dye has no issue, it can go anywhere, wherever there is a space, just keeps moving, and hopefully the spaces are also uniformly distributed, and therefore dye also gets uniformly distributed. It behaves like a solution, but in a solid state. So, there are some ways in which these interactions have been defined. You can do quantitative analysis also, that how much dye will go. An isotherm means that at the same temperature you are looking at how the dye moves from solution to the fiber, all right. Langmuir isotherms are the ones which are plotted at a constant temperature, Like we are not talking about the dyeing starting at room temperature, raise the temperature to a certain degree, then hold it to a certain degree for a certain degree at a certain time and then drop it down, those kind of things. Not, it is a constant temperature. So, at a constant temperature, at an equilibrium position, how much the dye is likely to be there in the solution, how much the dye is likely to be there on the fiber. Remember, this is an equilibrium reaction, equilibrium reaction. So, this particular isotherm Langmuir believes that there are sites available on the fiber where the dye is going to go. That means, if the sites are not there anymore, the dye will not go, right. So, this is the thing. Like the example we said is a wool, silk, even nylon with an acid dye. So, these are the amino end groups where the dye is going to go. If the end groups are finished, the dye cannot go. This is what this particular isotherm believes. This is the postulate. So, let us say you have a saturation point, let us we call it D, or what we have called here is S, which is saturation on the fiber, and so this will move and after some time it will not increase, right. And so, the sites are finished and therefore, dyeing will not take place, and so it's got from the kinetics you can get to this type of equation which will be valid if such interactions are there. Freundlich does not take into account as to that there are limited number of sites and therefore, it cannot go. So, I believe that there is an amorphous region where it will keep going, amorphous region and the crystalline regions are interdispersed uniformly, and therefore, the dye would keep on going, but the rate of diffusion would depend on how much the fiber initially has the dye and how much the solution has the dye. Therefore, the concentration of the dye in the solution and the dye on the fiber are defined by a power equation, which basically would give you some curve of a parabolic type. The value of k and n would differ from fiber to fiber, like dyes which do not actually depend on any site. So, fiber has many sites or areas amorphous, which is just go diffuse and enter there. So, as I said, some of the dyes will behave like this, but when the concentration become too high, the formulas may not really fit the way we want them to fit, but nevertheless mostly it is going to be true. The same power isotherm, when the value of the n becomes 1, so it just becomes dF is equal to k ds. So, it also has a saturation limit, but it goes straight as a straight line. So, based on what type of dye that we have, which does not depend on what is inside, what is outside, it just depends, it does not get governed by the inverse flow, and so the dye, as long as there is a space, it just keeps going. More is the dye in the solution, more will be the dye on the fiber in a linear way. So, when the n is equal to 1. So, this formula therefore, for you will be and this is the limit. After this there is no space, whatever the voids, the amorphous regions, they are also filled. Till that time, it will keep doing and follow the straight line, and this is what is we call as the solid solution. So, it will just keep following, and after that it will become flat. The previous one is this one you are talking about. This actually does not believe, it believes that the rate of absorption will keep going down as the dye and the fiber keeps increasing, and because it still thinks that there will be some bonding of hydrogen bond will formation or some kind of affinity things will be there, and so rate of diffusion will keep dropping down. This one says no, if there is space it will just go without bothering as to how much dye is already present till the time when nothing is available. So, it is a question of, for example, students entering through this room from this gate, there are enough seats available. It does not matter whether 10 students are inside and the 11th will be said, let us not go, because there are 10 students inside. Well, there are space, I just go, no resistance. So, it will just keep doing approximately like this. Of course, this slope of the curve is telling as to whether the dye loves the fiber more or the water more, right. This is also one of the reasons, although dispersed dye is not soluble in water, but still you dye from water. So, why do you dye from water? You could have dyed from a solvent where the dye is soluble. Why do you need to dye it from water where it is not soluble? Other dyes are water soluble, so it is very good. Here you do not want, because the water solubility was the one which was responsible initially that the new fibers like acetate fiber, polyester fiber, when they were synthesized or manufactured, those earlier dyes would not go in, and they found they are more hydrophobic. So, they have to have hydrophobic type of dyes. It is not a zero solubility, but very little solubility in water. Okay. So, if suppose we say tomorrow we want to dye from a solvent where the dye is soluble, and then dye the way you dye, let us say from an organic solvent like hexane, then you will find the dye goes. But the dye fiber interaction again is the same solid solution, all right. So, it will go sit in the fiber, but what you will find is the dye, because it is soluble in a solvent, it likes the solvent more. So, the partition coefficient will shift towards the solvent and not towards the fiber, and that is the reason why, although dispersed dyes are not water soluble, we still would dye from aqueous systems, right. So, it is good that more dye goes into the fiber rather than it stays in the solution. Now, this same type of colors, I am not talking about pigments at the moment, can be used for printing. How should they be different? One, many colors are being used in the same system, that of course. Mixtures are being used, yes. The fastness of the dyes in general has to be on the higher side, particularly the wash fastness should be on the higher side. Okay. and therefore, it will not be so much important that you have a faster rate of reaction. What will be more important is that it is uniform and properly diffused into the fiber, and proper diffusion, at least 50% of the fabric or a fiber cross section has been taken care of. And also the difficult part, as we said already, is the fastness of each of the mixture that you are using of the dye should be similar. It will be very difficult to be exactly same, because the molecule is different. So, theoretically you can expect that every different molecule will have a different property. But if it is in the range, we always talk about some range, acceptable limits, then it will work. So, you will have to depend a lot on the data sheet of the manufacturer and then select the mixtures, and not arbitrarily because this particular gives such a beautiful shade, let me use it. Later results will not be so nice. So, we just saying the same thing. Light fastness also, because you are going to be exposed, So, certain portions of the garment are exposed fully, certain portions of the garment are exposed less, and if the fading is not happening at the same rate, then the shade change takes place. And if the shade change takes place, then you can be quite sure people can find out there is a change of shade, it does not look the same. And so, we would have to, because such a costly process, we would like to select such dyes where light fastness is high, of course, and also similar, So, it is not easy, but you can try to find out, as I said, that how the fading takes place in your own ways. Whether if the dye fades, this fabric will get affected. A dye gets affected anyway, but do you think there are dyes which will affect the fabric? You can try and find out. There are some wear dyes which were stopped, the manufacture was stopped at some stage. Whether the substrate affects the fading, whether the substrate affects the fading. So, this is an important thing. One of the interesting case is there, and you can appreciate in the light fastness is, you are absorbing certain amount of energy. This energy is absorbed by the molecule which is called the dye. It does in any way absorbs, otherwise nothing will be seen, but you have UV light also, but not just the visible. So, if you absorb certain energy and that energy changes the molecule, damages the molecule, then obviously fading takes place. If suppose the energy, instead of the molecule actually changing itself, passes on this energy to the fiber, because the linkages are such that can actually transfer the energy. So, fiber, if suppose some damage takes place, will take place, but fiber being a large volume, large mass, it may be smaller. The dye is a small molecule just sitting somewhere on the surface and trying to do whatever, particularly surface. The fading will be felt on the surface. The dye which is inside the fiber deep is not even visible. So, you will not see whether it is faded or not, and most probably it is not even faded, right. So, we are looking at surfaces. Printing is based absolutely on surface, surface interaction with our own eyes, and that is how the printing takes place. And so, one case, for example, the cationic dyes, you can dye them on cotton also through a mordant. You can similarly print also. You can have those same dyes on acrylic fibers. Okay. Now, generally it was felt, and it may have been, you may remember also, the light fastness of the basic dyes on cotton were found to be relatively poor compared to even direct dyes, light fastness we are talking about. But the same dye, if applied on acrylic fiber, shows higher dye, higher light fastness, because you make an ionic bond there, it is relatively more easily able to transfer the energy to the fiber. A die feels safe, and so fiber die interaction can actually play some role in the fastness, defining the fastness, light fastness also. Wash fastness you understand very easily. There is a bond made, less bonding, more bonding, covalent bonding, ionic bonding. They will all play a wash fastness role in determining what is the wash fastness. But light fastness also gets affected. You can read more about it. The wash fastness, of course, is important. Higher the wash fastness, better it is as far as the printing is concerned. But you would be also very much interested in staining resistance. Staining resistance is important because when you wash, some of the dye solution during washing will flow over the areas where you don't want it to be there. And you must remember, stain is generally difficult to remove, easy to happen, because the equilibrium is in the favor of the staining, because the color is more in the solution, let us say, and there is no color on the fiber. Although temperatures of course are different, you are not giving the right pH, you are not giving catalysts, anything else, therefore, we do not expect so much to happen, but stain is a stain, and that is what you have to worry about. And so, one would like to have such dyes which do not stain easily. You will have to wash sometimes also. No? When you wash the same garment, it has got portions which are white, portions which are light, and so any time the dye can get exchanged. So, the staining is an important part. You will like to choose. Perspiration fastness, of course, are important because, and rubbing as well. So, if you have dyes which are not soluble, which have not reacted, which after process would be available in particles, even small, or dimers, trimers, and larger things, which become insolubilized after the process is over, they may have a tendency to get out also, because they may be on the surface. Let us say azoic, okay, they may remain on surface, and so the problem. Or the indigo, for example, you know the denim. So, affinity is less, does not penetrate more, but you like it anyway, and so rubbing fastness. Unless and until there is a fashion, it may not be very good. In the case of dispersed dyes, you should be bothered about sublimation fastness as well. You see, for the same reasons, the sublimation fastness is not very high. The wash fastness may be good because dispersed dyes are not water soluble. And let us say you have done the printing with dispersed dyes on nylon, which you can do. When you store also at temperatures which are not very high, but let us say go up to 50 degrees in some cases, you may see sublimation very low, but it is there, it is good enough to stain, and that is it, your print is over. The problem is not that how much dye you have lost, you have lost the whole fabric or a garment which you may have paid for. So, this is the general question is that do the dyes have all these fastness very good? They are not. Sometimes the shade you have to compromise, because the shade desires that such dyes must be used, otherwise you will not obtain, then you have to compromise. But everything not being same and not in your favor, still you have to work around. If you have the choice, you better exercise the choice. That is how we would like to call. So, let us say wet dyes, they are generally used for printing without any doubt. Okay. Why? They have all kinds of fastness which are very good, very important from the printing point of view. You look at the wash fastness, you look at light fastness, all kinds of fastness. They are very nice dyes, but they are expensive. So, you can appreciate anything which does everything right will be expensive, not just as a die, but also the whole process. You have reduction, oxidation, all that has to be done. So, they are good for printing, cost is high, so no problem, you should be able to use them. Which type of a fabric can be printed with wet dyes? Just give me some answer. What type of a fiber fabric? Cellulosic. Okay, very good. So, this type of a dye, the way it is, can be used for cellulosic, cotton, viscose, etc. If suppose somebody says, I want to use it for wool and silk, is the dye has a problem with the wool and silk? So, what is the problem? Alkali and the process is a problem, right? If suppose you can solve this problem, then you should be able to dye. That is why people made something called a solubilized wet dye. The same dye has been changed, that you have now groups attached, they make the dye soluble. So, these are sulfuric esters and sodium salts of sulfuric acid, because every time you make these compounds, you got to make a salt so that they remain ionic and so water soluble. So, it is the same dye as before, just that the structure has changed. So, because of this particular group that has been added, you are now here, this is the change from the previous dye, and suddenly this dye can be used on any fiber which is hydrophilic. Okay. So, you can go on silk, you can go on cotton, you can go on rayon, you can print on nylon, no issues. But why should you? That is a separate question. Cost is very high. Fastness, you would like to have any questions on the fastness? Do you think the fastness will be different? It should not be. It is the same molecule. If the molecule, because at the end of the day, this will become the same dye after final little oxidation cycle. It will be the same dye. And so, this is what we call as engineering a molecule to your own advantage. But cost is high, and of course, the palettes that are available, color palettes that are available, palette that is available is not as large as wide as the wet dye, but cost is quite prohibitive. But for printing purposes, if you really want it, they are there. So, all substrate can be used. Reactive dyes became very popular, right, and also for dyeing as well as for printing, because you have, let us say, something called this. So, you have a dye and a reactive group. Of course, there would be a bridging group and everything else. There is a chromophore, you can see this also will behave like one. And so, reactive dyes, everybody loves them. So, we spend some time here before we, they are water soluble, no issues on that, because they have various kinds of groups, which sulfonic acid groups is attached. So, what is the process? The process will be, first you dissolve, then you make a paste, after making a paste you do whatever, and then it must bond. So, you must provide a condition at a right time. If you provide the condition of fixation at the wrong time, then you get a wrong results. So, let us say it requires alkaline condition, the alkaline condition must be provided at the time of fixation. If suppose the alkaline condition, right alkaline condition is provided in the paste itself, a paste is stored for a long time, it is not made every minute and not easy to make also, it requires energy and effort. And therefore, what we will do? You will provide alkaline conditions at the right time. This particular dye is called a dichlorotriazenyl system, sometimes known as the M type of reactive dye. This is not used for printing generally. It is too reactive, lot of wrong things will happen, right thing will happen later. So, you want to create a condition, let us say it will fix at 60 to 80 degrees centigrade, then at room temperature it will not fix. So, whatever kind of material that you have, whatever anything else that you have, there will not, nothing will be happening at that time, it will happen at the time. So, you might prefer this dye, where one of the chlorine has been substituted by an amine. So, reactivity has gone down and time required, temperature required will be high, but for printing it is a good idea. Saving time is not a good idea. So, these are some of the reactive groups. As we said, the reactivity should be less, fastness obviously will be high, and this would, two things which we quickly talk about. The fastness, if the reactive dye has reacted with fiber, it makes covalent bond. So, should not have any fastness issue as far as the wash fastness is concerned, but if it has not reacted, then you have a problem. So, if you are looking at a cotton, where does it react? To the hydroxyl groups. Whenever there is a water, there is a hydroxyl group. So, it will react with water also. If it reacts with water, those, let us say one chlorine in a monochlorotriazine type of a dye was there, this will react with water, a dye will not react, it will just be there. You wash it, it will come out. So, fastness property would depend on how have you actually proceeded, whether most of the dye has reacted or most of the dye has not reacted or reacted somewhere else or in some other form, then you have a problem. Then this question of substantivity versus reactivity. So, you want it reactive, again moderate, like you said, I do not want a dichloro. Substantivity also moderate, that if at all it has hydrolyzed and is available when I do good amount of washing, it should come out. So, that the customer does not complain, it should come out while you are processing. If it is high substantive dye, then it will have different ways of bonding other than the covalent bonding also, like, and it will stay and keep coming out every time you wash. And so, the wash fastness sometimes reported may not be 5, it will be less than 5. How can you have? Reactive dye less than 5 means what? It means you have done bad job, dye has reacted with water and is available on the fiber, and so the new molecules will have moderate reactivity and moderate substantivity. So, that can come out. Which substrates can be printed with? Little louder. Which substrate? Yeah? Cellulose. Of course, they were designed for them, but wool, silk can be, and you do not really have to go to the alkaline pH also. They can react, and so hydrolyzed dye issues will also not be faced with silk and wool. So, they are one of the best actually in India also. A large amount of silk printing is done by reactive dyes, and so they actually show better fastness. they can react with free amino groups, end groups that are present in approximately neutral medium. You can do an acidic medium, but neutral is the best. And so, no hydrolyzed dye, because hydrolyzed dye is formed in alkaline medium. I think today we will like to stop here, and next time when we meet, take it further. Right? Thank you.
Hello everyone. So, we will continue with the topic measurement of ion linear density. In last class, we have discussed the various linear density expression systems like text, English count, metric count. Also, we have seen how to convert one count system to other system. We have also seen the relationship between one counting system to other system. Also, we have discussed the count system, how to get the resultant count. So, the resultant count for say direct system and indirect system, here if we see, we have discussed the indirect system, the resultant count are calculated based on the reciprocal of individual ion count. This was the system we have discussed. And for direct system, the resultant counts were calculated by simply adding the component ions count. And also we have discussed different practical problems, and how to calculate the resultant counts. So, here we have seen say 3 ply of yarn of same English count, how to convert it to 3 ply folded yarn count in text system. So, if we ply 350 any count, and ultimately we have seen the resultant count will be 35.42. Similarly, we have seen in direct system, suppose 36 filaments were there of 3 denier each monofilament, and we have seen the text count was 12 texts. Okay. In another problem, which was practical in industry, we face this type of problem where say 3 ply yarn of different types of yarn expressed in different system. So, in convention we have seen the worsted yarn is expressed in terms of NM, metric count in the industry itself, and polyester filament it is expressed in denier, and cotton yarn it is expressed in NE or NT. Okay. Here it is a NE. So, here the idea was, if we want to calculate the resultant count, first thing was that we have to convert the individual count to a single counting system, and best idea is to convert into a direct system. So, here as direct system text was there and we required in terms of text. So, we have converted all these counts into text system. Okay. So, 20, that means 50 NEM yarn, metric count yarn has become 20 texts, and 100 denier yarn has become 11.11 texts, and 60 NE yarn became 9.83 texts. Then simply we have added and this was the resultant count, that is 40.94 texts. Now, we will start how to measure. So, we will discuss different ways of measurement, different methods of measurement of yarn linear density. So, to measure the linear density, there are two basic requirements for determining the yarn count. So, why do we need to know the yarn count? It is that an accurate value of the sample length. So, if we have known mass, we have seen earlier, if we have known mass, so we need to know the actual sample length, actual length of the yarn, and that is actually required for many applications, and an accurate value of its mass, the accurate length of this mass, okay, of this its mass. Okay. So, what is the actual length of the particular mass of that? So, if we know the length of the yarn, what is the actual mass of this yarn? Okay. The yarns are available. So, for measuring count, the yarns are available in two forms. One is a continuous form, another is in cut form, small length. Okay. So, in package form, where the longer lengths are available. So, in suppose in bobbin form, where we have longer length. Okay. And in cone or cheese form, so longer continuous lengths are available. But and in this case we can measure the count in by using different measuring technique. But there are other situations where we do not have the package, we have small cut length, and we would like to measure the yarn count. Okay. In short or cut form, suppose we have a piece of fabric and we need to measure the yarn count. Okay. So, there are various systems. So, we will discuss one by one. So, yarn in package form, so continuous package form. So, we have longer length yarn available. When the yarn is in package form, such as ring bobbin or cone, it is usual to wind a number of skeins of by means of wrap reel. So, number of hanks, number of leads continuous of certain length by using wrap reel, if you want to measure the count. So, this is a wrap reel. Okay. This wrap reel, it is a simple machine which consists of a reel. Okay. There is it is a reel, a yarn package. This is the yarn package, it is a bobbin, ring bobbin is there, yarn package, okay, and package creel is there. The package creel will be there. This instrument has got, this is the reel on which we wrap the yarn, the creel where we place the package, maybe in the form of cone or in the form of bobbin, ring bobbin, yarn guide system. This is a yarn guide system, and this guide system has got little traverse. It moves sideways little bit, gradually it moves. So, that the idea here is that the yarn while wrapping, that the length of the every wrap, should be almost same. If there is no traverse, the problem would be that thickness of that particular place will keep on increasing, because yarn will be wrapped over the earlier layer. So, in that way yarn layer will increase. So, we will not get the actual length of the yarn. Our idea is to get the actual length of the yarn. So, in that case, if the traverse is not there, we will get the total different length, higher length we will get. A length indicator is there. Now, here length indicator does not actually measure the length of yarn which is being unwound. It is measured by the number of rotation of this wrap reel. So, if the wrap reel it has got a fixed circumference, the circumference of wrap reel is say 1.5 yard. Okay. So, a lee of say 120 yard requires say 80 such turn. Okay. So, after say 80 turn, there will be one indicator. Okay. So, there will be one indicator. So, warning bell will be there, and that immediately this we have to stop the winding, or in automatic machine it will automatically get stopped. So, after say 80 yard, 80 turn. So, 120 yard if it is yarn is known required. So, 80 turn will be required. Now, if we do not have the traverse, then the problem would be that even after 80 turn we will not have 120 yard, it will be little bit more than 120 yard, and when we will take the mass of that yarn, then we will get the wrong result. Okay. So, that is why it is very, and we have to take care that proper traversing is there or not, is there any jamming in traversing system or not, that we have to take care. And also the traversing, another advantage of traversing is that we have to, while taking out the lee from the wrap reel, if it is the yarns are wrapped one over other, it is a thick lee, thickness of the wrap is more, in that case taking out of lee will be difficult. Now, for cotton yarn, the reel has a girth of, that is circumference, this reel has circumference of 54 inch, that is 1.25 yards. Okay. So, that 80 revolution of the reel has skein of 120 yard. So, 120 yard is normally termed as a lee. Okay. So, 80 turn is there. So, we have got 120 yard. Now, the same lee we will have, we can just take the mass of that lee. So, mass of that lee we will get by electronic balance, and simply we can calculate the count system, and using the earlier formula, if we know the length of the yarn 120 yard, and if we take the mass, so 0.54 multiplied by length in yard 120 and divided by mass in gram. So, the yarn counting measurement system. So, there are in electronic balances they are direct yarn count system. So, in that system, in that particular instrument, the programming is there, the program is in such a fashion that it is actually you have to feed the length unit, how much yarn is there in the lee. So, if you feed 120 yard, and that will use this simple formula and directly give the yarn count in English count or maybe in text count. So, only thing you have to prepare a lee and just put and keep on putting differently, it will give the mean count, individual yarn count, it can calculate the standard deviation, it can calculate the CV percent, and it is linked with computer, and we can simply take the reading, okay, take the printout. So, with using this is not fully automatic. This is actually you have to take the Lee and you have to put on the electronic balance. Okay. And this wrap reel, it is it can be manual or it can be motor operated. Okay. So, after having say 80 turn, automatically it will stop. So, this is the first system, that is the using electronic balance, one can manually measure or this type of instruments are available. Second system where we use the wrap reel. Wrap reel is used to prepare the Lee, okay, and a Knowles balance is there. This balance is a special balance, it is called Knowles balance. Here we can directly read the count system, okay, and one should be aware that nowadays we do not use this system in industry, because the automatically actually electronic system is available, computer controlled system is available, directly we can get count, but in early days this Knowles balance was very helpful to get the direct yarn count system. Now, here the beam balance system is used, okay, behind which this is the beam balance system, normally balance system is there, okay, and behind which a separate rod of hexagonal section. So, one hexagonal section I can show you, this one is a hexagonal section, okay. In the hexagonal section, okay, is fixed, where out of 6 sides of hexagon, 5 sides are actually indicated with the different count range. Okay. So, out of 6, with the 5 of the faces lettered A to E. So, there are you can rotate these 5 faces. So, A, B, C, D, E, 5 faces depending on the count range. Suppose A section is count range in the coarser section, okay, maybe say so particularly say 1 to 5. So, different count systems are there, okay, at only in cotton system different count ranges are there. Okay. So, and say A being the coarser side and B is little bit finer range, in this way E is the finest count range. In that way at different range it is a gauged, it is actually marked at different count and engraved with the count scale, okay, to cover the certain range. So, certain range is covered. In the left hand of the pen, so left hand pen here, okay, a lettered weight. So, there are mass different weights are there. Okay. So, 5 such weights will be available A, B, C, D, E. Okay. So, when we will, and if we know the typical count, suppose we know a yarn it is around range of 50s. So, we will place that particular side, we will rotate that side and place that, rotate this hexagonal rod and place particular side. Suppose it is a C or that particular count range, we know the nominal count range. Okay. That count range we are placing that side and say C side, and corresponding to that side the C weight we have to place here in the left pan. Okay. And left hand pan lettered weight is placed, and on the beam again a small lettered rider will be there. So, there will be different rider of different letter. Okay. For A it will be A rider, B there will be B rider, like that. Okay. Suppose a cotton yarn is to be tested and its nominal count, its expected count is 36 count. Okay. So, in that case for 36 count range it comes out to be B. Face B of the scale is turned to the front, weight B is placed on the left hand pan and the rider B is put on the beam. So, on the beam we have to put the rider. So, this is the, here there will be rider, we have to put on the beam. So, a rider is there and the rider has to be shifted, okay, just to balance. Okay. So, the rider B put on the beam. Now, position of the rider to be adjusted until the beam is balanced with the skein of cotton yarn. Cotton yarn is put on the right side and there will be little bit unbalance. If it is unbalanced, so we have to shift the rider either left side or right side. So, to balance the yarn count, and then we can read the yarn count directly from the skein. So, here if it is the that is the range we expect. Suppose the yarn it is not coming to that range. So, then we have to shift if it is coarser or finer, we will come to know if whether it is a coarser or finer. In that accordingly we will shift to the other faces, we will change the weight, we will change the rider and in that way we will continue. This balance can also be designed with to suit the count system for other than cotton. Okay. So, one can always change the count system, one can depending on the count system, one can change the mass or weight or rider or the scaling. It is the best idea just to change the scale, one can directly get. Okay. Another system is that it is called quadrant balance. The quadrant balance again we can get directly the count system. This was used earlier, now again it is not being used. Earlier days the problem was that you have to take the length, you have to calculate and then that is why the systems were evolved just to know the quickly know the count system. So, quadrant system is that here a given length is measured. Okay. Here typically it is 120 yards for yarn and for sliver there is specific length, for roving there is a specific length. So, in this system we can measure for yarn, for sliver or for roving, okay. Specific lengths are there. Okay. So, for yarn, suppose in yarn it is a 120 yard, a given length is measured out by using the wrap reel. So, we can use either wrap reel or in wrap block we can use for sliver and roving. Okay. So, if it is yarn we use wrap reel, then after measuring that specified length then it is suspended from the hook. This is the hook. So, this is the yarn is specific length is measured using wrap reel or wrap block. Okay. Then it is suspended from the hook. So, this is the hook. So, we are suspending through the hook, okay. And specific mass is to balance here, it is available here, it is there. Okay. And it works on a beam balancing system, and the count is then read directly from the quadrant scale. This is the quadrant scale. Okay. This one is the quadrant scale. So, once we put the yarn here, this actually this needle will get deflected. Okay. Deflected. So, for a same length of yarn, if the length is, say it is a finer yarn, if it is suppose here it has been deflected here. Now, if it is coarser yarn, that means it will get deflected here. So, that means the counting system starts from this is showing finer yarn and then gradually it is becoming coarser. Here the idea is that we have to keep the length exactly fixed. Okay. So, that is it is simply by balancing system, it is a versatile system, okay, and this is actually we can do for yarn, for sliver, for roving, and also if we can change the scale, that scale we can just change in cotton system, for text system, for any other system we can do it. But in text system, in direct system, if we want to do, it will be on the reverse direction. Okay. It's so in cotton system it is and this that way we can always change the scaling. Okay. So, versatility of this system, okay, can be improved by engraving the scale with more than one series of values. So, what we can do here, one thing is that we can change the versatility by scaling for yarn, sliver and the roving, and also we can keep on adding different scales for different count system. For text, for metric count we can do. For example, one scale may read from 0.1 to 1. So, we have say 3 scales, one scale for 0.1 to 1 to give the hank of 4 yards of sample of sliver. Okay. So, this is just for example. Okay. If we know the range of the sliver, so it is assumed that its sliver count is 0.1 to 1, okay, hank 1 any. So, in that case, and for sliver we normally take it is a 4 yard for sample. For yarn we take 840 yards. Okay. And second scale, this is first scale, second scale is for roving and it is gauged from 0.1 to 6, that is the range of the count, range of the hank of roving 0.1 to 6, and here the standard length is 20 yards of length, sample length 20 yards of roving. Okay. And third one is for yarn, say 4 count to 80s count, and here 840 yards of sample. So, this 840 yard and it will give directly the yarn count. These scales are in the cotton count system. Okay. So, in quadrant balance it is normally in cotton count systems are available, but other quadrant balance are available for different range and different systems. So, different system, if we need to get the quadrant balance for directly for text, we can always get. Okay. Now, the yarn count for short length. So, if suppose we have fabric, so we can get the yarn count. So, for that some precautions we have to take. So, determination of the count of yarn in fabric is usually made on comparatively short length, okay, because always it is a piece of fabrics are available most of the cases, and also it is not possible to take out the longer length from the fabric. Okay. We cannot take 120 yards simply. So, after conditioning in the testing atmosphere, say 24 hours typically, 2 rectangular warp-way strip and 5 weft-way strips are cut from each cloth, from the cloth. So, why 2 only for warp? because the warp actually during warping we warp from individual cone. That means, individual thread represents one different separate cone. So, in that case, so two warp way strips will be enough to represent a number of threads, number of different cones, okay, enough. And 5 it is required, even more we may require, because majority of the weft within that strip may be from single cone, because it is a weft. Strips should be about 20-inch length. So, length of the strip should be around 20-inch and width is about that, so that it allows 50 threads to be taken out. So, that we need to take around 50 threads. So, 20-inch length and 50 threads we should take. Okay. So, the difference between warp and weft specimen arises from the fact, as I have discussed, that 100 threads from 2 warp strips. Okay. That means, 1 warp strip we are getting 50 threads. So, from 2 we are getting actually 100 threads, that is equivalent to 100 warping package. Okay. 100 different warping package and from reasonable randomness. So, we are getting, that means, if we take 2 strips, that is equivalent to the yarns from 100 package with randomness, okay, that is fairly random. But in weft way it may represent only 2 to 3 different samples. So, that is why we need a wide range number, larger number of samples. So, 100 versus 2. So, that means, here sample size is very narrow. Okay. Yarn removed from the fabric and then it may contain crimp. So, that means, we are not going to get actual length of the yarn. So, before we further proceed, we must measure the crimp, average crimp we must measure. And suppose, as we have seen, it is a 20-inch length. So, actual length of fabric, so actual length of yarn will be little bit more. That yarn length we have to get actual yarn length by calculating the or by measuring the crimp, and this correction by multiplying the correction factor, we can get the length of individual thread, and then we can calculate the total actual length. And here in this system we can use the micro balance, electronic balance, and we can take the mass, we can measure the mass and we can calculate the count of the yarn. So, for both warp and weft, because in weft normally weft direction crimp is high. So, in that case that we must use the correction factor, and this is the direct, it is not automatic system, it is not direct system, we have to calculate the count of the yarn. So, the yarns are then weighed accurately to calculate the count. So, in this system we have to use the electronic balance, okay. And here after that we have to manually calculate, because we cannot have program, then in that case we have to program, we have to feed the length. So, it is easy to calculate manually, okay. So, 100 threads are there. So, 100 threads we know, and we can calculate the total length and we can take the mass, okay. And this last process is that it is a Beasley balance. This balance here using small cut length we can measure the yarn count directly, and also in this method we can get the count of or number of yarn or yarn linear density in different measuring systems. Used to directly read the count when the sample size is small. So, we can directly get the count of yarn. Okay. The instrument consists of a simple beam. This is a simple beam. It's again it works on beam balance principle, and it's initially labeled. So, without any material or without anything, it should be labeled. Okay. And when it is labeled, this pointer actually bring the pointer opposite to a datum line. This is the datum line, this is the initial line. Okay. That shows the instrument is balanced. So, without any material, if the instrument is not balanced, that means there is something wrong with it, either with the labeling or with some that there is in the pivot section. This is the here in the pivot section there is some jamming. So, this beam should be freely moving. Okay. This it should be balanced. If it is not balanced, then this is the with this screw with balance system we can label. Okay. Now, this is the larger view where this is the balance and data line is there, and another this is separate one template will be given. This template shows that you have to cut the fabric of that length. So, small piece of fabric. So, this length, this longer length, this we can use for say cotton or linen. Okay. This is the linen. This one we can use for worsted or cotton. Okay. Half cotton. This one is for cotton or woolen system. So, different, this is for half cotton system. Okay. So, for different count, if we want to get the yarn number for a particular count system, we have to use this template. Okay. And then according to the size of the template, we have to cut the fabric. Okay. We may first mark the length, then we can cut the fabric. After cutting the fabric, then we have to carefully take out the threads. And another thing is that here one standard weight will be there, and which you have to actually hang on a notch of the beam arm on the pointer side of the pivot. So, there are two sides, this is side of the sample side and left side is pointer side. There is a notch is there, and where a standard mass is there, clip type mass, that we have to simply put on that, and that standard mass we have to that depends on your count system. So, different count system we can have different mass, and that when we are putting this mass, this and without any material, suppose a cotton system we have cut the sample and we have put the mass here. So, this pointer will be lowered because it is this side it has been heavier. Okay. Then a template is used to cut a short length of yarn. Okay, that we have to cut the fabric. Okay, short length of yarn, the length depends upon the count system. Okay, so for different count system we have different lengths. So, this is the for different count system, you can have different length. Then these short lengths are added one by one, okay, to the hook until the pointer is opposite side just exactly to the datum line. So, this is the thing. So, initially when there was no material here, we have put the weight, it has lowered down. So, after putting 1, it is not balanced, 2, 3, gradually we are going to put, we are putting the small length till it is balanced. Okay. So, for say cotton count, it's if we are gradually it is balancing, then we can get the count system directly, it is a count. Okay. The count is the number of short length required to balance the beam. So, that means this is the counts directly we are getting. When used in the analysis of small sample of fabric, the rough estimation of crimp has to be there. So, we must know the crimp value again, then only we will be able to get the actual length, okay, and then we can correct it. Okay. So, this correction is important, and then we can get the directly the yarn count system. So, here in this segment, in this topic, what we have discussed different count measurement system, and this count measurement systems are, we can have the yarn in different form, the continuous form, large package form, where we have enough yarn we can make Lee. Normally in count system we can take the Lee of 120 yards, and in also we have discussed for if we have smaller length of yarns available, okay, this may be in the form of fabric or in the form of small cut yarn sample. In that case, suppose we do not have the yarn 120 yarns available, we have smaller length of yarn available. In that case, we can use this systems of short length yarn counting system. So, knowing this yarn count, we can calculate the total length or total mass of yarn required. So, here now this is all about the yarn linear density measurement, and in next segment now we will discuss other topic. We will start with the tensile testing of textile material. Till then, thank you. Hello everyone, today we will start one new topic, which is tensile testing. In last classes, what we have seen, we have discussed that the yarn characteristics we can test by its linear density, or there are various other characteristics. Fiber characteristics we have seen, which we have seen that by length we can express, we can measure the length and related characteristics, length variation. Then we have seen that the fineness of yarn we can test by various methods, and maturity of cotton we have discussed, and then linear density of yarn. Now, in this topic we will discuss the tensile testing. Here tensile testing, it is actually divided into 3 distinct categories. One is in the tensile testing of fiber, next is tensile testing of yarn, and then tensile testing of fabric. So, 3 different measurement techniques, but if we see the basic principles, basic theories of all these 3 types of testings are almost same. We get similar parameters. We will discuss all these aspects in this session. So, why tensile testing of textile materials are important? Okay. So, why do you know, why do you want to know the tensile characteristics? It is just to know the level of strength provided by the material. Okay. What is the strength of the material? Okay. That we must know, because at which load it will fail, that it must know, but that particular value, it is very important for industrial and technical products. Okay. This is very important, because in those applications this strength breakage of material, it is extremely, we should know that it is extremely important to know, because that, like let us take example of rope. In rope, if we do not know the its breaking strength or stress strain characteristics, then it may fail during its actual use. So, any industrial application like filter fabric or maybe geotextiles, we must know the strength characteristics, its breaking strength, its elongation. So, all these characteristics we must know, but for apparel application, household applications, so this importance, although we must know the tensile characteristics, but its importance is not that, as in case of industrial textiles. Okay. So, because in household or apparel we never apply that level of force where it breaks. So, merely it is needed to, for adequate strength is needed. So, in during handling it should actually the product should not fail. Okay. In order to withstand handling during production and use, like we need that much strength of yarn, so that it should not break during weaving. So, that much. So, we if we have excess strength by imparting, by using various very sophisticated, very actually high tenacity fiber, that means we will unnecessarily add to its cost. So, for fabrics, for apparel application, we do not need that much strength, but for technical application, definitely for like composite making, we must use yarn or fabric with very high strength. So, in those applications it is extremely important to know the actual strength, even strength related characteristics. Now, let us see what are the factors which affect the strength of textile materials. First is that molecular structure of fiber. So, if the orientation, molecular orientation is high, then its stress strain characteristics will totally different, will change. So, higher molecular orientation will result better strength characteristics. Number and intensity of weak places. So, if the weak places are high, so basically strength of any material is the strength of its weak point. So, a yarn with say lower mean length, let us see this is the mean value. Okay. One yarn, this is the length along the yarn, okay, along the yarn. Suppose this is one yarn, even yarn, okay, even yarn, yarn A, another yarn which is uneven one, yarn B. Now, the yarn A has got, this is the strength value, okay, breaking stress. So, this yarn A, if we see theoretically at each and every point, okay, that the strength, it will be approximately same, because this yarn is uniform and number of fibers in the cross section of the yarns are same. So, this yarn has got almost uniform strength along the length at different point. If we test strength here at this point, at different point the strength will be almost same, but if we test the yarn B, suppose this yarn we have produced with a very good fiber, it is a very strong fiber. So, at different point this yarn strength will be different. Suppose mean strength is very high, okay. So, strength is higher than the strength A, strength of yarn A. So, but what we have observed that few points where due to unevenness there will be weak points are there, okay. So, few weak points are there, and when we test, it does not matter the other places, it is very strong, it will break only at the weak point. So, that is how the yarn will fail, okay. So, the number and intensity of weak places will result weaker yarn, okay. So, that is why the yarn which is uniform yarn with relatively lower strength is preferable, okay, and which is better than the yarn with higher mean strength, but it is non-uniform. Coarseness or fineness of fiber. So, coarser fiber will result, just let us see. So, cross section of two yarn, okay, A B of same count, yarn A is made of the coarser fiber, and yarn B is made of fine fiber. The linear density of these two yarns are same, as this yarn B is made of finer fiber. So, number of fibers are more, and also the specific surface area, surface contact of fibers in yarn B is much more than yarn A. So, that due to the finer fiber, so the yarn strength realization will be more in case of B. Third factor is relative humidity and temperature. So, as we know, textile material, most of the textile materials absorb moisture, okay, the hygroscopic in nature, and there are fibers like cotton which with the increase, with the absorption of humidity, the strength increases. But on the other hand, fibers like viscose rayon, after absorbing moisture, the strength drops. So, the relative humidity of the during testing, if it varies, then the for same yarn we will get different results. And also temperature, although not directly affect, but if it is too high temperature, very high temperature, then fiber may get degraded and it affect the strength. Also it is too low, at too low temperature, say sub-zero temperature, at that temperature. So, sometime few polymeric fiber they may be brittle and it affects the strength characteristics. So, relative humidity and temperature we must maintain. So, that is why it is suggested that to test the yarn or any textile material under standard atmospheric condition. Next is the elasticity. Elasticity also affect the strength characteristics of material. We will discuss all these characteristics. When an external force is applied to any material and it is balanced by the internal force developed in the molecular structure, okay. That is how we get stress strain characteristics. Man-made fibers are usually tested for their individual strength. So, the fibers we can test in two ways, in the single form and in the bundle form. Okay. So, most of the man-made fibers we get in the long continuous length form, that is why it is easy to test in the individual fiber strength. Okay. We can test as there is a very less variation in length and fineness of the. So, it is available in a long fiber and continuous condition, and in the man-made fiber another advantage is that it is a uniform in nature and in terms of fineness. Okay. So, as we have seen earlier, so this is a man-made fiber. Okay. And another is it is a natural fiber like cotton. Now, it is easy to test the fiber in the single fiber form. The advantage of man-made fiber is that its diameter wise towards the length wise it is totally uniform. Okay. So, across the total the diameter, the cross sectional shape or diameter is same throughout the length. But in case of cotton it varies. So, if we test the cotton in single fiber form, so it will always break at the weakest point, because variation in diameter, so variation in all these parameters fineness. So, it will always break in its weakest point. So, we will end up with a value which is much lower than its capability. And another reason is that here in man-made fiber, as I have mentioned, that it is available in continuous form. So, to minimize this variability, what we must do? We must take a number of fiber together. So, bundle of fibers we take together and then we test, like in bundle form. Suppose this is a cotton, we do not test the fiber in single form, because it is also very difficult to handle a single fiber of short length. Instead of that, we take a bundle of fiber, this is type bundle, then try to break the bundle and try to measure the bundle, and after that by simple calculation we can convert it to fiber tenacity, fiber strength characteristics. So, natural fibers are tested for their bundle strength due to high variation in terms of length and fineness. So, that is the reason why natural fibers are tested in bundle form. It may be cotton, may be jute, different natural fibers. Okay. So, in bundle strength, a bunch of fibers are put into a jaw, 2 jaws are there. So, by gripping with the 2 jaws, so bundle of fibers are put, then we try to break the fiber and measure the breaking strength. The jaws are moved out until the fibers are broken. The breaking load and elongation at break are noted. Okay. And tenacity of bundle in terms of gram per tex is measured, is equal to the breaking load in kg multiplied by length of the sample, length of the bundle. We can measure the length of the bundle, different test instrument, their bundle length is fixed. Okay. So, that if we know the bundle length of the bundle, and then what we have to do after breaking, we have to take the mass of the bundle. So, in bundle strength testing, we have to take the mass of the bundle, and then we can convert the strength in terms of gram per tex. So, there are various instruments, those who are measuring the strength and elongation characteristics of bundle. One of them is stellometer. Okay. In stellometer, the name came from strength and elongation, ST from strength, ELO is from elongation. So, the stellometer which measures the strength and elongation of fiber bundle and which works on pendulum lever principle. So, we will discuss the details in the principle of this instrument. Another instrument is there, it is a Presley fiber strength tester. Presley fiber strength tester also works also measures the fiber bundle strength tester, but here the working principle is the beam balance principle. Okay. It is a pivoted beam balance principle. So, these two instruments, stellometer and Presley fiber strength tester, their calculations are exactly same. Even their fiber jaws are interchangeable. Okay. So, that is why a bundle of fibers, that jaw is interchangeable. We can use the Presley jaw also in stellometer sometime. And another instrument that we have mentioned earlier also, in high volume instrument HVI, we test in bundle form, but not like the bundle will not be like Presley or strength a stellometer. Here bundle will be like the comb, directly the comb which has been used for the fiber length measurement, that same comb is used for breaking. It breaks the fiber in comb form. Okay. So, that is in bundle form. Okay. These are the three instruments which measures the fiber, particularly cotton fiber, in terms of in the form of bundle. Now, we will discuss the different terminologies which are used to express the tensile characteristics of textile materials, and these terminologies are, few terminologies are specially for textile materials, but many other terminologies, those are for in general any engineering material you can use. First is that breaking load or breaking strength. This is very general terminology. It is a load at which the specimen breaks. Okay. That is the breaking load. Simple, that is it measures for fiber, it is a centinewton or newton. So, that type of load, any load measure the, it is at which the specimen breaks. Then stress, stress for any engineering material with specific cross sectional area is measured by force per unit cross sectional area. Okay. But in case of textile material, as we have discussed already while discussing the fineness or linear density measurement, the fibers or any textile materials, they are not circular in nature or as a matter of fact of any normal specific size, neither it is circular nor rectangular, or it is the cross sectional shape is totally random. So, in case of textile material, we cannot use the stress in terms of cross sectional area, load per cross sectional area. So, cross section of fibers, yarns and fabrics are irregular. So, exact cross sectional area of fibers, yarns and fabrics is very difficult to measure. We cannot measure exactly. Okay. So, we cannot use the term in terms of the stress in terms of mass force per unit cross sectional area. So, this is the typical stress load elongation curve for any fiber or textile material. Okay. Now, try to see here, this is the typical curve I have drawn. So, and this curve is taken from almost this type of fiber. Okay. So, here this is the straight point where the load increasing with the elongation with the linear increase. So, this is the Hooke's region. Okay. After that it is a yield point, then after that there is again there is an increase in the stress load. Okay. And this is the breaking point, and at this point the material breaks. Okay. So, this point if we see, this is the breaking elongation horizontal distance, and vertical distance it is called breaking load. Okay. Let us see the animation here. This is elongation and this one is load. Okay. So, in load elongation curve, at the point where there is a sharp bend, it is called yield point. Okay. And this is a height, it is a breaking point, and here from x axis origin, this is the breaking elongation, and this is the breaking load, the y axis distance is breaking load. Okay. Now, if we see the stress strain curve, this one is the load elongation curve. If we see the stress strain curve, the nature is almost same, okay, and this the breaking point, at this breaking point this height is called tenacity. Here it is called breaking load, but here it is called tenacity, that is a breaking stress, other term is tenacity, and the horizontal distance is known as the breaking strain. So, this is the stress strain curve, okay, and we can easily convert the load elongation curve to stress strain curve, because if we know, so if we want to convert the load elongation curve to stress strain curve, what are the parameters required? We must know the initial gauge length, initial length. So, that we can calculate the load the stress from elongation, okay. And for calculating the stress we must know the linear density, and which linear density? Linear density, that is initial length. Always one should remember, here we have to divide the load with the initial fineness, initial linear density in text, okay. Because as we increase, as we extend the yarn or textile fiber textile material, the text value changes, okay, text value, but we do not take care of that part, we only divide by the initial linear density, okay. That is the process of measurement. Now, next is that specific stress, that is called mass stress. So, in as we have seen in textile material, we cannot measure the stress in terms of load per unit cross section. Here specific stress is measured by the, it is not the stress, we call it as specific stress or mass stress. In this case we do not divide by the cross sectional area, we divide it by the linear density. As we have seen, the linear density is proportional to the cross section. So, the value will be actually it is proportional, we will get the indicative value, but the actual, the numerical value may be different, but it is comparative value, okay. So, in case of textile material, the linear density is used instead of cross sectional shape. So, we can observe in fineness, we have observed that instead of cross sectional area we have converted it to linear density. Here also in stress we are converting the stress to specific stress, okay. So, it allows, it also allows the strength of yarn of different linear densities to be compared. So, suppose let us take one example, one textile material say of 10 ticks, 10 ticks has strength of say 100 Newton, okay. Now, another material of say coarser material of 20 ticks, it has got the strength of 160 Newton, okay. Now, how can we compare? If yarn was say 10 ticks and the strength was say 110 Newton, then we can say among these two yarn, so A, B, C, between A and B, so this A is stronger, okay, that we can say. But if we want to compare A and C, which one is stronger, because here the complexity is that it is of different linear density. So, to compare this, we convert this strength to the stress, mass stress. So, here the mass stress will be 110 by 10. So, that is 11 Newton per Tex, whereas this yarn C, it will have 160 by 20. So, it will have N 8 Newton per Tex. So, that means yarn A is stronger than yarn C in terms of specific strength, although the yarn actual breaking load is high. Actual breaking load is high in case of yarn C, but the which one is stronger strength wise, the yarn A is stronger, okay, because it has got higher specific stress. So, specific stress is equal to force per linear density, which is initial linear density. One should always remember it is the initial linear density, otherwise linear density always changes. Okay. Now, these are the different terminologies. So, yield stress, yield strain, okay. This is the yield stress, yield strain, tenacity, this I will just discuss. Okay. So, tenacity, what is that? The specific stress at break, that is the tenacity, okay, or specific stress corresponding to the maximum force. Okay. This we should remember. So, we normally get confused, that students get confused that which one is actual stress. Giving a curve, one has to actually identify, one has to calculate the specific stress or tenacity. Okay. Tenacity is specific, either specific stress at break or specific stress corresponding with the maximum force. Okay. Which one is higher, that is the stress. Now, we can see from these two curves. Okay. This is the with the this pink curve, we can see that is this is the breaking point. Okay, breaking. So, and breaking point is the highest point, that is why this stress we can call it as tenacity. But the curve with the blue curve, where after reaching the maximum point, this we always observe this type of behavior in particularly in staple yarn. After reaching this we observe for filament yarn. Okay. Then because after breakage starts, it does not break catastrophically due to sliding, the slippage of fiber, it also carries some load. Okay. So, after reaching to its maximum point where fibers start breaking, then still it carries some load, okay, for some time. So, here should we take the tenacity as this point or this maximum point? So, answer is that we should take the tenacity for this case as the maximum point. Okay. Next term is that breaking length. What is that? It is the basically the length of the yarn by its own weight, it will break. So, it is a theoretical value, theoretically it is a theoretical length in kilometer of specimen of yarn whose weight would exert a force sufficient to break the specimen. So, theoretically if we see, if we keep on unrolling from the space without any air disturbance, it is a vacuum, if we actually imagine. So, if we keep on unrolling and till the yarn on its own weight, when it breaks, the yarn that length is known as the breaking length, and it is expressed in terms of kilometer. So, that is why breaking length is actually termed as RKM. Okay. R came from the breaking. So, now let us see 10 Tex yarn breaks at a load of 150 gram force. That is the condition here. One 10 Tex yarn, it is breaking at 150 gram force. What will be the breaking length in kilometer? Okay, breaking length. So, let us see. So, breaking length would be 15 kilometer, because we can see here 10 Tex means 10 gram, okay, 10 gram of yarn length will be 1 kilometer, 1 kilometer yarn length 10 gram, okay. That means 15 gram, 150 gram is the force, gram force will have 15 kilometer. So, 15 kilometer is the 15 kilometer yarn will weigh 150 gram force. It will exert force of 150 gram force. Okay. So, that is why it is called, it is R came. R came from breaking, and km is kilometer. So, R km is the term which we use normally, and it is basically numerically the value is exactly same as that the gram per Tex. So, this is the gram force, it is gram force per Tex, this is the gram force 150, we divide it by Tex. So, 150 by 10 it is 15. So, these two terms are exactly same, and we can see in yarn trading nowadays it is called the breaking RKM value. So, RKM value means we do not actually measure the breaking length, we measure the gram per Tex and it is called RKM. Okay. Now, we must clearly understand the difference between strain and elongation. Okay. So, what is strain? Strain is the elongation by initial length, that the ratio of elongation and initial length, that is a strain which is actually unitless, but elongation has got the unit of the length, and extension percent or elongation percent, what is that? The elongation and the ratio of elongation and initial length multiplied by 100, this is the extension. These terms strain, elongation, these are used in all any engineering material, any material you can use, it is not specific for textile material. And what is breaking extension? That is the extension at which the material breaks. Now, what is gauge length? Gauge length is another term, it is the length between the jaws. Okay. Original length that of that portion of specimen under test. Now, let us see, suppose this is our fabric specimen. Now, what we do? We use jaws, top jaw, we have gripped here at the top and bottom. What will be the gauge length? Gauge length will be actual length of the specimens under test. So, we do not consider the total fabric length, this is the specimen length and gauge length is less than that. Okay. That is the gauge length, that is the original length of the material and between the jaws. Now, when it is extended, suppose it is extended to this point even before breakage, this has been extended. So, still this will be the gauge length, this gauge length is the initial length between the jaws. Now, let us try to understand clearly the details of stress strain curve. what are the different parameters. Okay. We will try to understand with the help of animation. So, here the terms are initial modulus, which is very commonly used in textile material, or Young's modulus. This is the modulus within Hooke's region, where stress is proportional to the strain, straight line. So, up to the point A, this is where there is a proportionality. In that region, if we measure the modulus, that will be the initial modulus. So, it is expressed in terms of, it is a tan theta, that means A dash vertical distance by A double dash. This is the ratio where which to express the initial modulus we can calculate. Now, if we extrapolate this curve, this line for easy calculation, that means B dash divided by B double dash. So, this is the stress divided by strain. Okay. So, that is this is the tan theta, okay. Initial modulus, the strain by stress. Okay. This one is the A dash. So, strain stress. So, this is A dash is stress and A double dash is strain. So, stress by strain we can get, this curve is stress strain curve. So, initially it is a straight line. So, that is why it is called initial modulus. Another term is called secant modulus. So, initial modulus is one parameter which is actually useful to get the stress strain characteristics at the very initial level, okay, just to the modulus, okay, to know the what is the tough modulus of the material. But during its stress strain path, one may like to know the stress strain, okay, modulus at any point. Okay. That means, the slope of stress strain line drawn between 0 point initial origin, okay, and the any specific point D, okay, of known stress or strain, that is called the secant modulus at that point. So, it is expressed at secant modulus at certain strain, okay, secant modulus of material at say x strain or x stress. So, again at this point we measure the stress divided by strain. Okay. So, that you draw the vertical line stress and then horizontal line stress by strain, that will give us the secant modulus. Now, let us see here. This is the typical stress strain curve. The line is being drawn, okay, with the along with the initial line. A dash is a stress and A double dash is strain. So, here we can see the initial modulus tan theta is A dash by A double dash, B dash or B double dash. Now, this is the point where sudden bend is there. Okay. So, that point is known as the yield point. Okay. This is the yield point and the distance. So, O C dash it is a yield stress. Okay. This distance is yield stress and O C double dash is the yield. So, O C dash is yield strain and OC double dash is yield stress. So, this is the yield point. Okay. So, we can calculate the yield stress and yield strain. This is called yield point. Now, a particular point is drawn. So, secant modulus, the slope of the straight line. So, this is exactly not showing, but slope of the straight line drawn between zone 0 and a particular specific point D. So, that is how we can get, although it is this animation is not showing the tangent, but it is a tangent we can take. It is a slope at any point. Oh, this is the slope. Okay. And here it is a breaking point. Okay. And this distance, so OE dash is the breaking strain and OE double dash is the breaking stress. Okay. So, these are the terminology we can derive from the stress strain curve. Now, OA elongation is due to, this is OA, this at during this zone OA, that is Hooke's region. Here the elongation is due to the stretching of primary or secondary bonds. Okay. That means, it is not breaking the bonds, it is here only primary and secondary bonds are being stretched. Okay. As there is no breakage of bonds, so this will come back, this will return, these are totally recoverable, and this is the Hooke's zone, which is called elastic zone. Okay. Because within this OA zone there is no breakage of bond. Now, once it crosses, what will happen? By further increasing the stress, the curve bends sharply at C, suddenly it bends, where large strain is occurring with the small increase in stress. So, that it bends towards the x axis. So, large strain is occurring with the small increase in stress. This particular point is known as yield point. Okay. And OC dash is yield strain and OC double dash is yield stress. And after this, after the yield point, a plastic flow occurs, breaking some secondary bonds. So, here there will be plastic flow. That means, if it increases, stress is increasing, then there whatever the deformation will be plastic deformation. So, it will not come back, okay, because there are breaking of some secondary bond. Okay. And during this, due to breakage, during the breakage of secondary bonds, the molecular rearrangement takes place. Okay. So, what happened? Molecule starts sliding, there will be excess strain due to small increase in stress, but molecular rearrangement takes place during that time. Once the molecular rearrangement takes place, that means molecules are becoming straightened and rearranged once again, then it will again try to impart some stress. So, that in that case the straining will be difficult. So, with the small strain again this stress will increase little bit. So, this rearrangement puts the material in a better position to withstand further stress. So, that means from this point onward. So, here the breakage is taking place. So, from C to say here D point, any other point, if it is asked what is happening between C to D. So, here what happens, the secondary bonds breakage starts, it takes place and molecular rearrangement is occurring. So, this rearrangement puts the material in a better position to withstand further strain. So, here the material is little bit in better position, then it's again it's increasing. So, otherwise what happened, if he in this point, so all the molecules starts breaking and the bonds start breaking, then it would have dropped here, it would have failed here, but here molecules are rearranged. That means it's again it has got capacity, it gets capacity to actually take more load. So, that is why it is again increasing. The nature of curve it varies depending on the molecular structure of fiber or yarn. So, depending on the molecular structure this nature of curve changes. So, there are various factors on which this the nature of curve depends. Okay. As the molecular orientation it is more, so then that means the curve will be totally little bit stiff. Okay. Like molecular, if we see the jute and cotton. Okay. Now, let us see. So, this is these are 3 fibers, natural fiber. This is for wool, this is for cotton, this is for jute. So, this difference in nature it is basically due to the molecular structure. Okay. So, depending on the molecular structure the nature of curve changes. See, wool, polyester, cotton, flax. So, it changes depending on the molecular structure. Flax has got very high modulus, okay, due to the structural orientation of molecule. So, we will stop here and we will continue with this in the next class. Thank you.
Alright, so we are meeting for the first class and this subject is called the advanced textile printing. Now, why we are calling it advanced is we believe that some printing you have already done and some new technologies which are there or some topics which may not have been covered at the undergraduate level. So, those are the kind of things that we will be covering and therefore, we are calling it an advanced printing technology. So, the important thing will be some of the content which has been described in brief, the detailed content of course is available. So, from the historical perspective, we will try to do a revision of the textile printing techniques and lay emphasis on little more emphasis on some topics and various printing styles and methodologies. And then we would of course have one topic. It's quite I believe that most of you may not have done the transfer printing, which is not so popular, but is getting more and more popular, which would have its scope, printing inks, the paper, the machine, conditions, some of those things which we'll cover. And then the digital printing, which is also becoming now popular. It's because of the cost that we find that most of the machines are not available as far as the production is concerned, but people are getting into it, and hopefully next decade would be a different decade. So their machines, the principles, various types of jet systems, the drop on demand, stability of inks, different classes of fiber, fabric, auxiliaries, etc. Pre-post treatment of the operation, and scale and economics. This is what may be interesting as far as course is concerned. So, we start with the lecture 1 in the conventional printing. So, obviously as we said that some of you have done textile chemistry undergraduate, some of you have not, and therefore those who have not done, they will have to work harder in a different way to catch up with the rest of the class. But we will spend some time revising what you have done in the undergraduate, and also some of the topics which you may not have done, and we will discuss them as well. So, we revise what is printing. Okay, this is one important thing that we would like to know. What is printing? Essential ingredients in a printing paste, basic steps involved in printing, styles and methods. This is in terms of, let us say, the areas in which we will spend. So, before we take printing, let us try to revise, and you will help me. What are the basic unit operations in chemical processing of textile, the whole gamut starting from the grey fabric to the finished fabrics. So, what would be the first process?
Grain inspection.
What do you say?
So grain inspection.
Inspection. Well, that is an inspection part of it. There is not really much of a preparation. Good. Any other?
Shearing and cropping.
Shearing and cropping, which probably may have some similar operations of this type. And why do we do this process?
Remove protruding fibers.
Right. So, we remove protruding fibers, and this process is quite important from the point of view of printing, because when you have lot of protruding fibers and you do a printing by any method, there is always a chance those fibers will also get some paste, and when you lift a roller or a screen, they may also jump, and when they jump, then they will do something which you do not like. And so, from printing point of view, it is a very important process. And what is the next process? Okay. So, why do we do desizing? Remove size. So, this is a necessary evil that we do, which is called sizing. This has nothing to do with the natural, it is a man-made problem which has been created, but it was important for them to do that. And so, various processes, whether enzymatic or non-enzymatic processes, are used to remove the material that you have added during the preparation or during weaving. And then scouring. So, this scouring is not for every fiber as such, but every fiber will have a different reason for scouring. Cotton probably is one of the most important ones, which requires a lot of scouring. Why do we do scouring?
To remove oil and fat material.
So you have various oil, fatty materials in the thing, and you would like to remove, so that the next processing becomes good. And one of the reasons why you are looking at it is the wettability of the material. So you want to increase the wettability, because whatever chemicals that you want to add, you want these chemicals to diffuse into the fiber and then do proper reactions and proper bond making, so that you get either dyeing or a chemical finishing or whatever. This will be good if you do scouring. How do we test whether scouring is good or not? Right. So you can put a drop of water on the fabric, or there are tests which are sinking tests and so on and so forth, which can tell you as to scouring is good or not. Next process could be, right. So when you look at bleaching, again this bleaching is also different for different kind of fibers. I mean, you're looking at cotton as a thing, but if you have wool, if you have silk, you have polyester, if you have any other kind of material, so you will be looking at different kind of bleaching agents. Most important bleaching agent is? All right, so this is called the hydrogen peroxide. So oxidative bleaching agents are there, which you will use depending upon which fiber that you have. Next, all right. So if you look at mercerization, this is also very specific to only cotton. If you have other fibers, let's say viscose, do you do anything? You don't do anything, of course not mercerization, but there is a process called causticization, right? So which also is important for diffusion of chemicals into the fiber. And so, but mercerization is specific to only cotton. Can you mercerize wool? Why not? So it will just get destroyed, dissolved in the alkali. Even mild alkali can dissolve. This is too strong an alkali for wool silk, and therefore this process is very specific. So when we talk about unit operation, so every fiber will have a different unit operation, right? It's not that one single thing is going to work for everyone. And then of course dyeing, which is most interesting unit operation, which adds lot of value. Now most of the people who are sitting here, or you meet them, there will be very few who wear only white, right? So they get identified, but large number of people would be wearing some colored clothes, and the dyeing becomes an important part. And so all things related to the chemistry of the fiber, the chemistry of the dye, their interaction becomes important. And so we would like you to remember, you will be doing some course in this. And then we come to our topic, which is called printing, right? One of the most important unit operations, because it adds a lot of value. And finally, a finishing, which also is a general term, different fibers, different finishes, and itself is a big area in which various types of functional properties can be imparted in onto the textiles. So let's say we are going to be concentrating on printing. This is what the thing is, and that at the moment we are looking at conventional printing. So value addition, as we said, that unless and until you see color, the customer would not like to touch anything. You go to a shop, when you start looking at it, you look at the colors and you get impressed by them, and then the one who has made it asks for more money. So the value addition happens quite a lot when you do printing, and depending upon what kind of print, which is a personalized print, then obviously the value is very high, only for you. and if it's a mass produced print, then obviously the cost is less and therefore the value also is less. Therefore, one is looking at printing as an operation coming to all the unit operation that you saw. This has to be right first time. There is nothing you can say, well, doesn't matter, we will try to repair. When you do something in the wrong in the dyeing, that is, say, the depth of shade that you wanted is less, so you can top it up. It costs, but you don't have so much of a wastage, you can top it up. If you find the depth of shade is little high, you have a stripping mechanism, so you can strip it up. If you find the errors are too many, then you can say, well, I'll do another dyeing with deep shades, dark, black, blues, reds, and suddenly you will find, well, the value can still be recovered. You can't do in printing. If you've done something wrong, there is no way you can correct it. You can't take a brush and start doing something, right? This is therefore a difficult, printing is a difficult unit operation. It's not easy. Finishing, first of all, people can't even find if there is a fault. Let's say you are doing a wash and wear finish, and how can anybody find whether the wash and wear finish is very up to the mark, or there is a variation, or there is something else? Just go. The complaints will come after 1 month, by the time thing is gone, but not that complaint should come. But right first time, every time is printing. Any textile operation, starting from making of a fiber to the making of a yarn, the variations are there and people accept some variations, this is okay. But if you do something wrong, you say, okay, it's going the seconds, it's going the thirds. If you make this mistake here, the chances are there will be nobody to pick up the thing, and that's a real loss. There is no correction that you can do. And this is difficulty. If non-experts can find your fault, then you can't sell it. In many other things which are, let's say, finishing, which adds lot of value, non-experts can't tell you what is the fault. Here they can tell, because there is a design which looks like a design, there are many colors there, and so if one color goes out of its boundary, people will know it's come out of the boundary, because you did not set it properly, you could not print it properly, and that's it. And you can't correct it, so you have lost the value, just like that. So the difficulty levels are others also. In dyeing, for that matter, dyeing is also something where people can find some fault, but not like printing. As I said, we can correct it also. In this case, you actually use more than one color. So when you say that I am printing, so you are not talking about one color or one shade. So you have more than one shade, same green but different compounds. And so getting to many things in different areas of the fabric and hoping everything will be fine, and you say, I want to match the shade. How do you match the shade? You will get the result only after you have completed the printing process. Till the time you have not completed the printing process, there are many ingredients around. They themselves play various role in showing you what color you are seeing. Becomes very difficult. The shade matching, let's say computerized color matching systems are very nicely, beautifully used for dyed material. For printing material, even if you get a shade, well, this part of the green is to be like this, that part of the green must be that, this must, red must be this, and the blue must be that, and all of them must match. It's a very, very tough thing. And therefore, those who actually handle the printing department are really big names. They are really good experience. They understand when the fabric is running at 50 meters per minute and they can find a fault and they say stop the machine. Something has to be done. So, it is a very serious business. As I said, non-experts can tell you, you are wrong. And fastness, which fastness are we talking about? Every time we talk about a shade, this shade has been made by mixture of dyes, not one single component. And when you mix, you can make errors there. When you choose the mix, this time you had one type of dye, a green, the other type, another type of green. They're supposed to be similar, but they're not same. Okay, so you match them. But even if you match the shade in your own, from your own perspective, then what do? You like them to wash fastness. All the dyes can give you the shade, but they may not have the same wash fastness. So, when you have a dyed material or maybe from a single component dyed material, when you wash, something goes out, the shade may keep decreasing, depth of shade may keep going down, but you may still be able to survive, because most of the time we will not remember what was the original shade. Even lab of course will know. In this case, something which appeared to be a particular type of a blue is now a different type of a blue, because one of the components gone more, other is still there. The mix is changing. Similarly, when you look at a light fastness, one may be fading faster than the other. So, what you see is a change of tone happening. A change of tone is much easily identifiable compared to the loss of depth. And so, it becomes much more difficult. The selection, which dye has to be selected, how it has to be applied. So, you are looking at a fastness first, you are looking at a light fastness first, you are looking at a shade first, then you want to match the shade. And then you also find if you make a mistake, somebody will find out. It is very difficult. So, you must appreciate any product which is a printed product and actually you are liking it, then somebody has worked very hard. So, as an engineer you should appreciate almost every product, but I am now telling you a printed product is definitely something which you should be proud of and should appreciate and thank the guy. It is quite possible the people who head the printing department may be actually getting higher salary, at least in the private sector, compared to the finishing guys or the dyeing guys, simply because if they make mistake, company loses straight. So, they have to be right, and so right kind of people they accept. Of course, experience is the one which helps. Now, let us say whatever somebody said is printing. Of course, we understand at different points something is happening. They call it sometimes localized dyeing. Printing itself is there, term which we are trying to understand. You say now it is like dyeing.